So, here's something worth thinking about as you settle in tonight. Right now, in this exact moment, thousands of invisible waves are passing through the walls of whatever room you're in, through the blanket you're lying under, through you. They're carrying music, conversations, weather data, text messages, GPS coordinates, a time signal from an atomic clock in Colorado, and probably a few hundred Wi-Fi packets that make up someone's late-night Netflix stream. You can't feel any of it, not a single one. They're sliding through your body right now, the way light passes through glass. And you will never, not once in your entire life, directly sense them with any organ you were born with. And yet, these waves, these radio frequency waves, might be the single most transformative thing human beings have ever learned to create and control. More than steel, more than concrete, arguably more than fire, because fire you could stumble on. But radio you had to imagine first, and then prove, and then build from almost nothing. Let's talk about that. Let's start at the very beginning, before anyone had the faintest idea that invisible waves were even possible, and work our way forward slowly through the story of how we figured this out. And it is a story, a really good one, full of rivalries and dead ends, and a few moments of genuine, breathtaking insight that changed everything. But before we get to the people, let's just sit with the idea itself for a moment. You are lying right now at the bottom of an invisible ocean. FM radio is passing through you at frequencies around 100 megahertz. Cellular signals at 700, 850, 1900 megahertz and more. Wi-Fi at 2.4 and 5 gigahertz. GPS. Signals from satellites orbiting about 12,500 miles above your head. Signals that left those satellites about 67 milliseconds ago, traveling at the speed of light. Bluetooth. Digital television. Police and fire radio. Aircraft transponders. Weather satellite downlinks. And the quiet hiss of the cosmic microwave background, the remnant radiation from the Big Bang itself, stretched by the expansion of the universe to microwave frequencies, washing over you right now, just as it washes over everything, everywhere, all the time. All of these are electromagnetic waves. Every single one of them is described by the same equations that a Scottish physicist wrote down on paper in 1865. All of them are ripples in the same invisible field that fills all of space. And all of them coexist in the same room, the same air, the same nothingness, without interfering with each other, because each one occupies its own tiny slice of the vast electromagnetic spectrum. And here's what we're going to talk about tonight. We'll start at the surface of this ocean, with the things you use every day, Wi-Fi, your cell phone, Bluetooth, and slowly sink downward, layer by layer, to what lies at the very bottom. Along the way, we'll figure out a few things that sound simple but actually took centuries for people to understand. What actually is a radio wave? Not metaphorically, not simplified, but physically, literally, what is it? Why can some waves pass through walls while others can't? Why can you hear FM radio in a tunnel but lose your GPS signal? Why do AM radio stations use towers hundreds of feet tall while a Wi-Fi antenna is a little plastic stub? How can you possibly encode a human voice, or a video, or a stream of data into an invisible wave traveling at the speed of light? Why is empty space, a strip of nothing, a slice of the electromagnetic spectrum that you cannot see or touch, worth billions of dollars? And strangest of all, how is it that your phone, a small device that fits in one hand, simultaneously runs about a dozen different radio systems, each on its own frequency, each with its own modulation, and none of them interfere with the rest? Each of those questions has an answer, and each answer connects to the others in ways that aren't obvious until you see the whole picture. The reason your phone's antenna is tiny has the same root cause as the reason AM radio towers are enormous: wavelength. The reason Wi-Fi doesn't cross a city has the same root cause as the reason a shortwave signal does: ionospheric reflection.
The reason spectrum costs billions is a direct consequence of Shannon's theorem from 1948, a piece of mathematics that draws a line in the sand and says, "This far, no further." So let's begin. And let's begin not with anything human, but with something very, very old. We're not going to rush. We'll just go together, layer by layer, deeper into this invisible ocean. No hurry. Let's see where it takes us. And by the end, you'll see the world around you a little differently. Because it has always been filled with these waves. You'll just know they're there now. Let's not start with people. Let's start with something much older. Right now, as you lie here listening, radiation that is 13.8 billion years old is passing through you. It's older than the Earth, older than the sun, older than every star you've ever seen in the night sky. It appeared when the universe was so young and so hot that atoms couldn't exist yet. All matter was a superheated soup of subatomic particles, and space was opaque, flooded with blinding light, like the inside of a star. And then, about 380,000 years after the Big Bang, the universe cooled enough for electrons to bind with nuclei. For the first time in history, atoms formed. Matter became transparent, and that blinding light that had filled all of space broke free. It began to travel, and it's still traveling. But over 13 billion years, the universe expanded enormously, and that light expanded with it. Its wavelength stretched. From visible light, it became infrared radiation, then microwaves. Today it arrives as a faint, uniform glow at a frequency of about 160 gigahertz, with a temperature of just 2.7 Kelvin, a hair above absolute zero. This is the cosmic microwave background radiation. And here's what makes it remarkable for our conversation tonight. It's a radio wave. Physically, it's the exact same thing as the signal from your Wi-Fi router. The same ripple in the same electromagnetic field, obeying the same equations, just at a different frequency from a different source, and as old as the universe itself. Think about what that means. The electromagnetic field, that invisible fabric in which all radio waves live, was not invented by humans. It didn't appear when Marconi built his first transmitter. It has existed since the very beginning of time. The universe has been filled with electromagnetic waves for 13 billion years before the first human picked up a stick. The field was always there. Humans didn't create radio waves. They learned to whisper into them. Let's sit with this a moment longer. The cosmic microwave background was discovered accidentally in 1965 by two radio engineers at Bell Labs in New Jersey, Arno Penzias and Robert Wilson. They were testing a large horn antenna, originally built for satellite communications, and they couldn't get rid of a persistent low-level hiss in their receiver. They cleaned pigeon droppings out of the antenna. They checked every cable and connector. They pointed the antenna at New York City, thinking urban radio noise might be the culprit. Nothing helped. The hiss was there no matter which direction they pointed. It was coming from everywhere, uniformly, all the time. They eventually realized they were hearing the remnant radiation from the birth of the universe. The signal that had been traveling for 13 billion years, stretched by cosmic expansion into the microwave band, was being picked up by their antenna and showing up as a faint, steady noise. Penzias and Wilson won the Nobel Prize for this in 1978.
And here's what's beautiful about it in the context of our conversation. They found the oldest electromagnetic wave in the universe using the same basic technology, an antenna connected to a sensitive receiver that Hertz had used 80 years earlier to detect the youngest. The physics doesn't care about the age of the signal. Maxwell's equations treat a wave from the Big Bang exactly the same as a wave from your microwave oven. The field doesn't distinguish. It was there before stars existed, and it'll be there after the last star dies. It simply is. And everything we've built, every radio station, every cell tower, every satellite, every radar, is a temporary pattern of deliberate ripples in a field that has existed since the beginning of time. We're whispering into something ancient and vast, and our whispers travel outward at the speed of light and never quite stop. And that's a beautiful thought to keep at the edge of your mind as we go forward, because the story we're about to tell, how humans discovered this field, learned to generate waves in it, learned to load those waves with information, and learned to build machines that listen, spans several centuries. And it begins at a moment when nobody on Earth had the slightest idea that electricity and magnetism were even connected. Imagine the world before 1820. Electricity was one thing. You knew it from Leyden jars and voltaic piles, lightning, static shocks, frog legs twitching from current. Magnetism was something entirely different. Compass needles pointing north, lodestones sticking to iron. Two different chapters in the textbook, two different forces of nature, no connection. And then, on one specific day, in one specific lecture hall in Copenhagen, something happened. Small, almost accidental, and absolutely everything changed. But before we get to that moment, remember our first big question. What actually is a radio wave? We're about to find out. Because the answer was hidden inside a compass needle and a piece of copper wire. Hans Christian Ørsted was a professor of physics at the University of Copenhagen. 42 years old, broad forehead, neatly combed hair. He wasn't a brilliant theorist, and he wasn't an exceptional experimentalist. But he had one idea that wouldn't leave him alone. He suspected that the forces of nature ought to be connected. That electricity, magnetism, light, heat, all of these might be manifestations of something unified. It was more of a philosophical intuition than a scientific hypothesis, and his colleagues didn't take it seriously. But Ørsted couldn't shake it, and so, in the spring of 1820, during a lecture, and historians still debate whether this was a planned demonstration or a happy accident, he placed a compass needle near a wire carrying electric current. The needle moved. Not toward the wire, not away from it, sideways, perpendicular. Think about how strange that is. If the magnetic force had been directed toward or away from the wire, like gravity points toward a mass, that would have been understandable. But the needle turned crosswise, as if an invisible whirlpool were spinning around the wire. It meant that electric current creates a magnetic field that wraps around the wire in a ring. Electricity creates magnetism. Physically, right there in front of his students. The news spread across Europe within months. In France, André-Marie Ampère seized on it immediately. Ampère was brilliant and intense, the kind of person who could barely eat or sleep when a problem had him in its grip. Within weeks of hearing about Ørsted's discovery, Ampère had worked out the mathematical relationship between electric current and the magnetic field it produces. He showed that two parallel wires carrying current attract or repel each other depending on which direction the currents flow. He was essentially proving that magnetism could be entirely explained as a consequence of moving electric charges. That was a huge deal. Two things everyone thought were separate, unified. At least in one direction. Electricity makes magnetism.
But the obvious question hung in the air. Does it work the other way? Can magnetism make electricity? That question tantalized everyone who thought about it for about a decade. And the person who answered it was Michael Faraday, one of those figures in the history of science who almost feels like he was written by a novelist. Faraday was born in 1791 in South London. His family was poor. His father was a blacksmith who was frequently ill. Faraday had almost no formal education. He left school at 13 and was apprenticed to a bookbinder. But he read the books, everything that came through the shop. The ones about science captivated him.
He started attending public lectures at the Royal Institution, including a series by the famous chemist Humphrey Davy. Faraday took meticulous notes, bound them beautifully. He was a bookbinder after all, and sent them to Davy with a letter asking for a job. Davy eventually hired him as a laboratory assistant. And from that position, with no university degree, no mathematical training to speak of, Faraday became arguably the greatest experimental physicist of the 19th century. What Faraday did in 1831 was show that a changing magnetic field induces an electric current. Not a static magnet sitting next to a wire, that does nothing. But move the magnet, push it through a coil of wire, and current flows. Change the magnetic field, and electricity appears. This is electromagnetic induction, and it's the principle behind every electric generator and every transformer on Earth today. Every single one. The power plant keeping the lights on in your room right now, or charging the device you're listening to this on, works because of what Faraday figured out in a basement laboratory in London nearly 200 years ago. It's worth pausing on what Faraday accomplished, because it's easy to rush past. Here was a man with almost no mathematical education, who through sheer experimental brilliance and visual imagination arrived at a picture of reality that turned out to be more correct than the mathematical models of his formally educated contemporaries. The prevailing view in the early 19th century was action at a distance, the idea that electric charges and magnets somehow exert forces on each other across empty space instantaneously without any intervening mechanism. Newton's gravity worked this way. The sun pulls the earth pulls the sun, and nobody worries about what happens in the space between them. Most physicists applied the same framework to electricity and magnetism. Two charges attract or repel across empty space. End of story. Faraday found this deeply unsatisfying. His experiments with iron filings sprinkled around magnets, those patterns of curved lines radiating from pole to pole, convinced him that something real existed in the space between charges and magnets. The space wasn't empty. It was filled with a physical entity, a field that carried the force and transmitted it at finite speed. This was radical. It meant that what happened at point A didn't instantly affect point B. Instead, a disturbance at A propagated through the field, reaching B after some delay. If you suddenly moved a magnet, the effect wouldn't be felt instantly across the room. It would travel outward at some speed, rippling through the field like a wave across water. Maxwell made this precise. His equations showed that Faraday's fields obeyed specific mathematical rules, and that disturbances in the field propagated at exactly the speed of light. The field wasn't a vague philosophical concept. It was a mathematically exact physical entity with its own dynamics, its own energy, its own momentum. This idea, the field, turned out to be one of the deepest concepts in all of physics. It underlies not just electromagnetism, but all of modern physics. quantum field theory, the standard model of particle physics, general relativity's treatment of gravity as the curvature of space-time. Every force in the universe is now understood as mediated by a field. And it all started with a bookbinder's apprentice in London, sprinkling iron filings on a piece of paper and seeing patterns that the mathematicians had missed. But Faraday did something else, something more subtle and in some ways more revolutionary.
Because he wasn't a mathematician, he couldn't describe his discoveries in equations the way Ampere could. Instead, he thought in pictures. He imagined invisible lines of force spreading out from magnets and charges, filling the space around them. He called them lines of force, and he thought of them as real physical things, not mathematical conveniences, but actual structures in space. Most established physicists of his day thought this was a bit naive, maybe even embarrassing. The serious people worked in equations, in action at a distance. The idea that empty space was filled with invisible lines seemed almost mystical. But Faraday was right. He was more right than almost anyone realized at the time, because those lines of force, that picture of fields filling space, that turned out to be the key to everything that followed. It's worth pausing to appreciate just how far Faraday's thinking was ahead of his time. In an era when the dominant scientific worldview treated forces as acting instantaneously across empty space, action at a distance, the idea that one magnet pulls on another through nothing, with no intervening mechanism. Faraday insisted that something physical filled the space between objects. He couldn't express it mathematically, but his physical intuition was extraordinary. He actually performed an experiment that hints at why his picture was right. He sprinkled iron filings around a magnet and observed how they arranged themselves into curved lines connecting the poles. Those curves, he argued, were real. The space wasn't empty. It was structured. The magnet didn't reach across the void and grab the filing. It created a field, and the filing responded to the field at its own location. This distinction between action at a distance and field theory seems like a philosophical quibble until you realize its consequences. If forces act instantaneously at a distance, there's no reason to expect waves.
Waves require a medium, something that can be disturbed locally and pass that disturbance along. But if space is filled with a field, then a disturbance in the field at one point can propagate outward through the field, point by point, at a finite speed. That's exactly what Maxwell's equations describe. The field is the medium, the wave is a disturbance in the field, and the speed of propagation, the speed of light, falls out of the equations naturally from the measured properties of electricity and magnetism. Without Faraday's stubborn insistence that fields are real, Maxwell might never have found the equations that predict electromagnetic waves. The bookbinder's apprentice, who imagined invisible lines of force in the space around magnets, made the radio in your pocket possible. 200 years later, the lines of force he imagined are as real and as important as he always said they were.
We just call them electromagnetic fields now. And the person who took Faraday's intuitive pictures and turned them into perhaps the most beautiful set of equations in all of physics was James Clerk Maxwell. If this story has a single pivotal character, a hinge on which everything turns, it's Maxwell. Born in Edinburgh in 1831, the same year Faraday discovered induction, which is a lovely coincidence, Maxwell was in many ways Faraday's opposite. Where Faraday was self-taught and visual, Maxwell was formally educated and deeply mathematical. He studied at the University of Edinburgh and then Cambridge, where he was recognised as one of the most gifted mathematical minds of his generation. But Maxwell had something that pure mathematicians sometimes lack. He had physical intuition. He could see the physics inside the math. and he took Faraday's field idea seriously when many of his peers didn't.
Starting in the early 1860s, Maxwell set about translating Faraday's lines of force into rigorous mathematical language. He gathered up everything that was known about electricity and magnetism: Coulomb's law, Ampere's law, Faraday's law of induction, the fact that magnetic monopoles don't exist, and unified them into a single framework. 4 equations, that's it. 4 equations that describe all of classical electromagnetism. You might have heard them called Maxwell's equations, and they are, without exaggeration, among the most important equations ever written by a human being. Let's try to get a feel for what these 4 equations actually say, without the math. The first equation says, electric charges create electric fields. Positive charges push the field outward. Negative charges pull it inward. More charge means stronger field. This is Coulomb's law, rewritten in field language. The second equation says, there are no magnetic charges, no magnetic monopoles. You never find a north without a south. Every magnet has 2 poles, and if you cut it in half, each half has 2 poles again. Magnetic field lines never start or end. They always form closed loops. The third equation says, a changing magnetic field creates an electric field. This is Faraday's law of induction, the principle behind every generator and transformer. Move a magnet near a wire, and current flows. The fourth equation says, a changing electric field creates a magnetic field. This is the crucial addition that Maxwell made. Ampere had shown that electric current creates a magnetic field. Maxwell realized that even without current, a changing electric field does the same thing. Now look at what happens when you put the third and fourth equations together. A changing electric field creates a magnetic field, fourth equation. But that magnetic field is itself changing, which creates an electric field, third equation, which is itself changing, which creates a magnetic field, which creates an electric field. On and on, leapfrogging through space. That leapfrogging pattern is an electromagnetic wave. It emerges from the equations as inevitably as ripples emerge when you drop a stone in water. Maxwell didn't design it or assume it. He just wrote down the laws of electricity and magnetism as accurately as he could, and waves appeared in the solution. The universe contained electromagnetic waves whether anyone was looking for them or not. Maxwell's equations just revealed what was already there. And the speed of that leapfrogging, the speed at which each cycle of electric creates magnetic creates electric propagates, is determined entirely by 2 measured constants, the permittivity and permeability of free space. When Maxwell plugged in the measured values, the speed came out to the speed of light. That wasn't an input, it was an output. He didn't assume light was electromagnetic.
The math told him so. This is why physicists consider Maxwell's equations one of the greatest achievements of the human mind. From a careful description of how charges and magnets behave, the existence and speed of light emerge as consequences. The unity of electricity, magnetism, and optics, 3 apparently separate phenomena, was there all along, hidden in the data, waiting for someone to write down the right equations. But here's what's really wild. When Maxwell wrote down these equations and started working through their implications, he found something nobody expected. The equations predicted the existence of waves, self-propagating disturbances in the electromagnetic field that would travel through empty space. An oscillating electric field would create an oscillating magnetic field, which would create an oscillating electric field, and this leapfrogging pattern would radiate outward, carrying energy with it, requiring no medium, no wire, no physical connection.
and when Maxwell calculated the speed these waves would travel at, it came out to about 193,000 miles per second, which was, within the margin of experimental error at the time, exactly the measured speed of light. Think about what that means. Maxwell didn't set out to explain light. He was trying to unify electricity and magnetism, but the math told him unavoidably that electromagnetic waves exist and that they travel at the speed of light. His conclusion was as bold as it was inevitable. Light itself is an electromagnetic wave. Maxwell published his full theory in 1865 in a paper called A Dynamical Theory of the Electromagnetic Field. He was 34 years old, and buried in that theory, waiting to be found, was the entire future of radio, television, radar, cell phones, Wi-Fi, Bluetooth, GPS, satellite communication, everything we're discussing tonight. Because Maxwell's equations don't just predict waves at the frequency of visible light. They predict electromagnetic waves at any frequency. The whole electromagnetic spectrum was there, implicit in 4 lines of mathematics, 2 decades before anyone figured out how to actually produce or detect these waves deliberately. But Maxwell himself never got to see that happen. He died in 1879 at 48 of abdominal cancer, the same disease that had killed his mother at the same age. He knew his theory predicted these waves. He believed they existed, but he never saw experimental proof. That proof would come from someone else, in a physics laboratory in Germany, and it would involve sparks jumping across tiny gaps in metal, a loop of wire on the other side of the room, and one of the most elegant experiments in the history of science. The man who performed it was Heinrich Hertz. Quiet, meticulous, precise. Born in Hamburg in 1857 into a well-to-do family, his father was a lawyer who later became a senator. Young Heinrich was one of those kids who was good at everything: languages, woodworking, drawing, mathematics. Physics pulled him in, and he ended up studying under Hermann von Helmholtz in Berlin. Helmholtz saw something in Hertz and pointed him toward the big, unsolved question of the day. Can Maxwell's predicted electromagnetic waves actually be demonstrated in a laboratory? The challenge was enormous. You can't see these waves. You can't hear them. You can't feel them. You need to somehow create a disturbance in the electromagnetic field that's strong enough and fast enough to launch a wave into space. And then you need some kind of receiver sensitive enough to notice that wave arriving. In the 1880s, you didn't have electronics. You had wire, metal, glass, and your own ingenuity. Hertz's transmitter was beautifully simple.
Picture 2 metal spheres, each about the size of a large marble, mounted on short rods with a tiny gap between them, a few millimeters, connected to an induction coil that steps low voltage up to very high voltage. When you crank it high enough, a spark jumps across the gap. And that spark isn't just a flash of light. It's a sudden, violent surge of current, oscillating back and forth across the gap at millions of times per second. According to Maxwell, any accelerating electric charge should radiate electromagnetic waves. So that little spark should be broadcasting waves outward in every direction. His receiver was even simpler. A piece of copper wire bent into a loop, almost a complete circle, with a tiny gap at one end. Another pair of small spheres separated by a fraction of a millimeter.
If electromagnetic waves from the transmitter reached this loop, they would induce a tiny oscillating current, Faraday's induction at work again. And if that current was strong enough, a miniature spark would jump across the tiny gap. So Hertz was literally looking for sparks. Tiny, barely visible sparks in a darkened room. And he found them. Between 1886 and 1888, Hertz demonstrated that when he fired up his spark gap transmitter, sparks appeared in his receiver loop across the room. No wire connection, no physical contact, through empty space.
Maxwell's prediction, made on paper 20 years earlier, was real. But Hertz didn't stop at demonstrating the waves existed. He proved they behaved like waves, like light. He showed they could be reflected off metal surfaces, refracted through a prism of pitch. He demonstrated interference, two waves overlapping, reinforcing or cancelling each other.
He even measured their wavelength by creating standing waves and walking along with his receiver, noting where the sparks were brightest and where they vanished. From the spacing, he calculated the wavelength. From the wavelength and the known frequency, he calculated the speed. The speed he got was the speed of light. Hertz had proved that light and these new waves were the same fundamental phenomenon at different frequencies. Maxwell's unity of electromagnetism and optics wasn't just elegant mathematics, it was physical reality. It's worth lingering on Hertz's experimental method because it reveals something important about how science works at its best. Hertz didn't just show that waves existed, he systematically demonstrated that they had every property Maxwell's equations predicted. For his reflection experiments, he used a large sheet of zinc, about 6 feet by 3 feet, positioned at various distances and angles from his transmitter.
By moving his receiver loop around the room, he could map out where the reflected waves were strongest and weakest. The patterns matched exactly what you'd predict from optical reflection. Angle of incidence equals angle of reflection, confirming that these invisible waves followed the same geometric rules as light. For refraction, he constructed a large prism out of pitch, essentially hardened tar, a material that's transparent to radio waves but has a different refractive index than air. When he directed his waves through the prism, they bent, changing direction just as visible light bends when passing through a glass prism. He could measure the angle of bending and calculate the refractive index, which matched theoretical predictions. His standing wave experiments were particularly clever. He placed a metal reflector at one end of the room and generated waves from the other end. The incoming and reflected waves overlapped, creating a pattern of nodes, points of zero amplitude where the waves cancelled, and antinodes, points of maximum amplitude where they reinforced. Hertz walked slowly along the room with his little receiver loop, noting where sparks appeared brightly, antinodes, and where they vanished, nodes. The spacing between successive nodes was exactly half a wavelength. From this spacing he determined the wavelength. Combined with his knowledge of the oscillation frequency of his spark gap, he could calculate the wave's speed. The care and thoroughness of these experiments is extraordinary when you consider the tools he had. No oscilloscope, no signal generator, no spectrum analyzer. Nothing electronic at all. Just metal, wire, glass, pitch, a darkened room, and eyes trained to see barely visible sparks across a gap of a fraction of a millimeter. It's the equivalent of building a particle accelerator from kitchen supplies.
And the results were so precise, so systematic, and so beautifully aligned with Maxwell's predictions that even the most skeptical physicists were convinced. Hertz's published papers from 1887 and 1888 are models of scientific clarity. He describes every apparatus, every measurement, every source of potential error, with a transparency that makes his experiments reproducible from his written descriptions alone. Reading them today, more than a century later, you can follow his reasoning step by step and see exactly how he established each point. It's science at its finest, patient, rigorous, and ultimately decisive. And here's where the quiet tragedy comes in. When someone asked Hertz what practical use these waves might have, he reportedly said something like, "It's of no use whatsoever. This is just an experiment that proves Maestro Maxwell was right." He saw no application. None. He couldn't imagine, and perhaps nobody could have imagined in 1888. that these waves would become the foundation of an entire world of communication. Hertz died in 1894 at 36 from granulomatosis with polyangiitis, a rare autoimmune condition affecting blood vessels. He never saw the first radio transmission. He never heard a human voice carried on the waves he discovered. The unit of frequency, the Hertz, 1 cycle per second, is named after him. And every time you see a number followed by Hertz on your radio, your Wi-Fi router, or your phone's specs, that's a small monument to a man who proved something beautiful and was gone before anyone understood what it meant. Now, who invented radio? The question of who took electromagnetic waves from laboratory curiosity to practical communication is one of the messiest priority disputes in the history of technology. In Russia, Alexander Popov independently built a receiver very similar to Marconi's and demonstrated it in May of 1895. In the United States, Nikola Tesla had been lecturing about wireless transmission and filed patents on radio circuits. The US Supreme Court posthumously restored Tesla's priority on key radio patents in 1943. Oliver Lodge in England demonstrated wireless signal transmission over about 500 feet at a lecture in 1894. The truth is that the technology emerged from the work of many people. But Guglielmo Marconi, a 20-year-old Italian with no university degree and an extraordinary instinct for practical engineering, was the one who most aggressively turned it into a working, commercial, world-changing system. And that system would force us to confront every single one of those big questions we asked at the beginning. How do you load information into a wave? What happens to a wave as it travels? Why does the size of an antenna matter? And why is the spectrum finite? We'll take them one at a time. But first, we need to understand what makes one wave different from another. And since we mentioned Marconi, let's stay with him a moment longer, because the story of the transatlantic transmission deserves more detail. It's one of the great engineering gambles of the early 20th century. By 1899, Marconi had formed the Wireless Telegraph and Signal Company and was selling equipment to the British Navy and shipping lines. And England was the right place to be, because England had something Italy didn't: a massive navy. The British Empire in the 1890s was held together by ships, and ships at sea had a communication problem as old as seafaring itself. Once a vessel sailed beyond the horizon, it was effectively cut off. Submarine telegraph cables connected continents, but a moving ship couldn't tap into those. Semaphore flags and signal lamps only worked within line of sight. A ship in distress, a fleet needing to coordinate, an admiral wanting to issue orders, all depended on physical proximity. The idea that you could send a message from ship to shore, or from ship to ship, without any physical connection, using invisible waves traveling at the speed of light, that was not just exciting, it was almost unbelievable. And the British Admiralty, to their credit, recognized its potential almost immediately. Marconi's first public demonstrations in England were dramatic. In 1896, he gave a series of demonstrations for officials from the British Post Office, which at the time controlled telegraph communications. He sent signals across distances that kept growing, first a few hundred feet across a rooftop in London, then across Salisbury Plain, about 2 miles. Then in May of 1897, across the Bristol Channel, a stretch of open water about 9 miles wide. Each time the signal arrived, each time the little coherer at the receiving end responded to the invisible waves, and the Morse code message was decoded successfully. Here's the thing about Marconi that you have to understand. He was 22 years old during these demonstrations. He didn't have a university degree. He hadn't published papers. He wasn't part of any academic establishment. And yet he was standing in front of senior British government officials, showing them something that some of the finest physicists in the world hadn't bothered to pursue as a practical technology. After the Atlantic crossing, Marconi established regular transatlantic wireless telegraph service. The technology spread rapidly. By 1912, hundreds of ships carried wireless equipment, and Marconi's company dominated the market. The wireless operators on the Titanic worked for the Marconi Company.
It was Marconi equipment that sent the distress signals that brought the Carpathia to rescue 710 survivors. His system worked beautifully over distances of 50 or 60 miles, which was already revolutionary for ship-to-shore communication. But Marconi wanted more. He wanted to send a wireless signal across the Atlantic Ocean. He chose Poldhu on the southwest coast of Cornwall for his transmitter. The antenna was suspended between two wooden masts, about 200 feet tall. The transmitter power is hard to pin down from surviving records. Estimates range from about 10 to 25 kilowatts, but it was enormous by any standard of the day. The spark gap was so loud it could be heard for miles. On the receiving end, Signal Hill, Newfoundland, Marconi flew his antenna on a kite. The wind was strong and unpredictable. Kites kept tearing free, and the whole enterprise teetered on the edge of chaos. On December 12, 1901, after several days of failures, Marconi heard, or said he heard, 3 faint clicks in the telephone earpiece connected to his receiver. 3 dots, the letter S. Physicists were skeptical. Some believed Marconi might have mistaken atmospheric noise for a signal. Others flatly denied transatlantic transmission was possible. Calculations showed the Earth's curvature made it so, and indeed, if radio waves traveled strictly in straight lines, the signal could not have crossed the ocean. But Marconi didn't know that, and as so often happens in history, ignorance allowed him to attempt what the knowledgeable considered impossible. The explanation came later. In 1902, Oliver Heaviside in England and Arthur Kennelly in the United States independently proposed the existence of a conducting layer in the upper atmosphere that could reflect radio waves back to Earth. This was the ionosphere. It was experimentally confirmed in the 1920s when Edward Appleton proved ionospheric reflection, for which he received the Nobel Prize in 1947. Now, there's an important subtlety about the question, who invented radio, that's worth exploring further. Nikola Tesla, by the early 1890s, was already lecturing about wireless transmission of information. Tesla was thinking bigger and wilder than almost anyone. He envisioned a global wireless system, not just point-to-point telegraphy, but a kind of world broadcasting network. He filed patents related to radio apparatus in 1897, and the US Patent Office initially granted Tesla priority on certain radio circuits before Marconi. The legal tangle between Tesla and Marconi dragged on for decades. In 1943, the US Supreme Court posthumously restored Tesla's priority on key radio patents. Tesla had died earlier that year. Oliver Lodge in England had actually demonstrated wireless signal transmission before Marconi. He sent signals about 500 feet at a lecture in 1894. But Lodge didn't push it toward real-world communication. He was more interested in the science than the engineering.
Marconi was the opposite. He didn't care about proving Maxwell right. He cared about sending messages. The truth is that radio emerged from the work of many people, building on Maxwell and Hertz. What Marconi uniquely brought was relentless practical focus, the determination to make the technology work over real distances, in real conditions, for real customers. That's a different kind of genius, and it's the kind that changes the world. Before we continue the story, and it gets much more dramatic, I promise, let's pause and look at the wave itself up close. Because the words frequency, wavelength, and amplitude are going to come up again and again. If they stay abstractions, everything else becomes a fog of unfamiliar terms, and we don't want that. So, this is where we answer the first of our big questions from the beginning. What actually is a radio wave? At its most basic level, it's a ripple in the electromagnetic field. Think of dropping a stone into still water. Concentric rings spread outward. The water itself doesn't travel across the pond, the wave does. Each little bit of water just bobs up and down in place, but the pattern of that bobbing moves outward, carrying energy as it goes. A radio wave does something similar, except instead of water molecules bobbing, it's electric and magnetic fields oscillating, taking turns pushing each other forward through space. The electric field creates the magnetic field, which creates the electric field, which creates the magnetic field, on and on, leapfrogging forward at the speed of light.
And there's a crucial detail. The electric and magnetic components of the wave are always perpendicular to each other. Always. And both are perpendicular to the direction the wave is moving. If the wave is coming toward you, the electric field might oscillate vertically, while the magnetic field oscillates horizontally, or vice versa. But they're always at right angles. This, by the way, defines what's called polarization. If the electric component oscillates in the horizontal plane, it's a horizontally polarized wave. If vertical, it's vertically polarized. Polarization is determined by the electric component, not the magnetic one. And it matters, because a receiving antenna works best when it's aligned with the electric field of the incoming wave. A vertical antenna catches a vertically polarized signal best. A horizontal antenna catches a horizontally polarized one. That's why turning an indoor TV antenna 90 degrees can kill the signal. You've moved the receiving plane out of alignment with the transmitter's polarization. Now, frequency. This is possibly the most important word in our conversation tonight. It describes how many times per second the electromagnetic field completes a full cycle of oscillation. One full cycle, from zero up to maximum, back through zero down to minimum, and back to zero again. If that happens once per second, the frequency is 1 Hertz. 1,000,000 times, 1 megahertz. 1,000,000,000, 1 gigahertz. Your household electricity oscillates 50 or 60 times per second, 50 or 60 Hertz. An AM radio station broadcasts at about 1 megahertz, 1,000,000 oscillations per second. FM radio, about 100 megahertz, 100 million times per second. Wi-Fi, 2.4 gigahertz, 2,400,000,000 times per second. And visible light, hundreds of trillions of hertz, 3 orders of magnitude higher still. And all of them are the same phenomenon, the same physics. Maxwell's equations draw no distinction between a radio wave and a beam of light. The only difference is frequency.
Wavelength is the distance a wave covers in one full cycle. Freeze the wave in space, like a photograph of an ocean swell. The distance from one crest to the next, that's the wavelength. And here's the critical relationship. Frequency and wavelength are inversely related. Higher frequency means shorter wavelength. Lower frequency means longer. They're linked through the speed of light. The formula is simple. The speed of light equals frequency times wavelength. For practical radio calculations, wavelength in feet is roughly 984 divided by frequency in megahertz. Want the wavelength of FM radio at 100 megahertz? About 9.8 feet. Wi-Fi at 2.4 gigahertz, 2400 megahertz, about 5 inches. AM radio at 1 megahertz, about 984 feet. 9.8 feet, 5 inches. 984 feet. Feel the difference? We'll come back to this, because the size of the wavelength determines an enormous number of practical things. How long your antenna needs to be, whether a wave can pass through a wall, whether it bends around buildings, how far it can travel. Amplitude is the maximum displacement of the wave from zero. On a drawing, it's the height of the crest. Amplitude is related to signal power. Bigger amplitude, more energy carried. As you move farther from a transmitter, amplitude shrinks. The wave thins out, getting weaker until a receiver can no longer distinguish it from noise. So, 4 basic characteristics of any electromagnetic wave. Frequency, how fast it oscillates. Wavelength, distance per cycle. Amplitude, strength of oscillation. And polarization, plane of the electric field.
Plus speed, which in a vacuum is always the same, about 186,000 miles per second, the speed of light. Let me explain why this matters so much with a concrete example. Think about sound waves for a moment, because the analogy is useful. A deep bass note from a subwoofer, maybe 50 Hertz, with a wavelength of about 22 feet, can travel through walls and around corners in ways that a high-pitched whistle cannot. You can hear your neighbor's bass through the wall, but not the treble. The longer the wavelength relative to the obstacle, the more the wave bends around it or passes through it. Radio waves follow the same pattern. AM radio waves at 1 megahertz have wavelength of about 1,000 feet, far larger than houses and trees and hills. They flow around obstacles like water around pebbles. You can receive AM radio in valleys, behind buildings, in places where there's no direct line of sight to the transmitter.
FM radio at 100 megahertz has wavelengths of about 10 feet, still big enough to partially bend around structures, but you start noticing signal loss behind large buildings. Wi-Fi at 2.4 gigahertz has wavelengths of about 5 inches, much smaller than walls and furniture. It can still get through drywall and wood reasonably well, but thick concrete and metal are serious barriers. And millimeter waves at 28 gigahertz, with wavelengths of less than half an inch, are blocked by almost everything. A hand, a leaf, a pane of glass with metallic coating. This wavelength versus obstacle relationship isn't a quirk. It's a direct consequence of diffraction, the same physics that governs how ocean waves bend around a breakwater or how sound bends around corners. The wave notices obstacles that are comparable to or larger than its wavelength. Obstacles much smaller than the wavelength are nearly invisible to it.
And this single principle explains an enormous amount of practical radio behavior. Why AM can reach you in a basement. Why FM works in your car but not in a parking garage. Why Wi-Fi works through one wall but not 3.
Why 5G millimeter wave works on the street but vanishes indoors. It also explains something else. Why lower frequencies travel farther. It's not just that they diffract better around obstacles, it's also that they lose less energy interacting with the environment. Higher frequency waves scatter more, are absorbed more by atmospheric moisture, and interact more strongly with materials. A wave that slides past obstacles without noticing them loses less energy than one that has to push through or bend around each one. That's it. 4 numbers, and you've fully described a wave. But from those 4 numbers comes an astonishing diversity of behavior. And here's where we begin to answer our second big question. Why some waves pass through walls while others don't?
A radio wave at 300 kHz with a wavelength of over 3,000 feet behaves completely differently from a wave at 28 GHz with a wavelength of about 0.4 of an inch. Even though both are radio waves, both obey the same Maxwell's equations. One bends around mountains, the other can't get through a wet piece of paper. Actually, let's take this further, because the electromagnetic spectrum is one of the most beautiful organizational ideas in physics, and it deserves a proper look. Imagine a piano keyboard that stretches from one wall of a room to the other, but instead of 88 keys, it has billions. At the far left, the lowest notes, extremely low frequency radio waves oscillating just a few times per second, with wavelengths measured in thousands of miles. These are so long that they require antennas miles in length and can only carry the most basic information, a few characters per minute. The US Navy once operated a VLF transmitter in Wisconsin with an antenna system that covered 41 square miles. 41 square miles of wire strung between towers to generate waves long enough to reach submarines lurking beneath the ocean surface. Move right along our imaginary keyboard. The frequency rises, wavelengths shrink. We pass through the AM broadcast band around 1 MHz, wavelengths of 1,000 feet. Through shortwave at 3 to 30 MHz, wavelengths from 300 feet down to 30. Through FM radio and television around 100 MHz, wavelengths of about 10 feet. Through the cellular and Wi-Fi frequencies in the hundreds of megahertz and low gigahertz range, wavelengths of a few feet down to a few inches. Through the millimeter wave bands at 30 to 300 gigahertz, wavelengths of about half an inch down to about a 25th of an inch. And then we cross an invisible line, and we're in the infrared.
Our radio waves have become heat radiation. Your TV remote control operates in the infrared, around 300 terahertz. Keep climbing. The wavelengths shrink past 1,000th of a millimeter, past a 10,000th, and suddenly we're in the visible spectrum. Red light, orange, yellow, green, blue, violet. The entire rainbow of human vision occupies a shockingly narrow band, from about 430 trillion to 750 trillion hertz. After a journey from waves miles long, the visible spectrum is just a tiny sliver, barely an octave of the electromagnetic keyboard. Keep going past violet light and you enter ultraviolet, then X-rays, then gamma rays, electromagnetic waves of such high frequency and short wavelength that they interact with matter at the atomic and subatomic level, ionizing atoms, penetrating tissue, causing biological damage. Same equations, same physics, same field. Just frequency, cranked up to extremes. The entire electromagnetic spectrum, from waves that take minutes to complete one cycle to gamma rays oscillating quadrillions of times per second, is one continuous phenomenon, described by one set of equations, predicted by one theory. What we call radio waves is simply the lowest frequency portion of this spectrum, the portion we've learned to generate and detect with antennas and electronic circuits, rather than with light bulbs and eyeballs. And the boundaries between categories, radio, microwave, infrared, visible, ultraviolet, X-ray, gamma ray, are human conventions, not physical transitions. There's no moment where a radio wave becomes an infrared ray. The frequency just keeps increasing, the wavelength keeps decreasing, and the way the wave interacts with matter gradually shifts. The categories are useful labels for engineers and physicists, but nature doesn't recognize them. To the electromagnetic field, it's all the same thing, just ripples, at different speeds of oscillation. And now that we understand what a wave is, we can return to what people did with them. Because the answer to our third big question, how do you encode a voice or a video into an invisible wave, turns out to be one of the most elegant ideas in the history of engineering. And it directly answers our third big question. How can you possibly load a human voice into an invisible wave? We left off with Hertz proving that electromagnetic waves exist and saying they were completely useless. The question had shifted from, do these waves exist, to, can we make them carry something? Marconi answered yes. Starting around 1894, experimenting in the attic of his family's villa near Bologna, he improved on Hertz's apparatus and added a crucial element. A long, vertical wire connected to the ground, an antenna. By 1895, he was sending signals nearly a mile across his father's estate. By 1897, across the Bristol Channel, about 9 miles of open water. By December 12, 1901, he claimed to have received a signal across the Atlantic Ocean, from Poldhu in Cornwall to Signal Hill in Newfoundland, about 2,100 miles of open water. Most physicists thought it was impossible. Radio waves travel in straight lines. The Earth is curved. Over 2,100 miles, the straight line goes far out into space. The wave should miss Newfoundland entirely. But the signal arrived. 3 dots, the letter S in Morse code. How? Nobody understood for another 20 years. The answer was the ionosphere, a layer of ionized gas in the upper atmosphere, between about 40 and several hundred miles up, that reflects certain radio waves back to Earth. Marconi's wave didn't fly in a straight line. It bounced off the ionosphere like a ball off a ceiling. We'll come back to this in detail. But Marconi's signals were just dots and dashes, Morse code. The next question was, can you send a voice? That happened on Christmas Eve, 1906, when Canadian inventor Reginald Fessenden transmitted the first human voice and music by radio. Ship radio operators along the Atlantic coast, accustomed to hearing nothing but Morse clicks in their headphones, suddenly heard speech and violin music. They were, to put it mildly, startled. Fessenden's breakthrough was a different kind of transmitter. Instead of the crude spark gap, which created chaotic broadband bursts of energy, Fessenden used a high-frequency alternator, essentially a very fast electrical generator that produced a smooth, continuous wave at a specific frequency. This clean carrier wave could then be modulated. Its amplitude could be smoothly varied in proportion to the sound picked up by a microphone. The result was the first true amplitude modulation broadcast. The Christmas Eve transmission of 1906 is worth imagining in detail.
Fessenden's transmitter was at Brant Rock, Massachusetts, on a 220-foot tower. He played "O Holy Night" on a violin, read a passage from the Bible, and wished his listeners a Merry Christmas. Radio operators on United Fruit Company ships in the Caribbean and along the Atlantic coast, men who had spent months hearing nothing but the staccato clicks of Morse code, suddenly heard music and a human voice coming through their headphones. Some thought they were hallucinating. Others thought their equipment was malfunctioning. A few wrote letters describing the experience. It's hard to overstate how disorienting this must have been. Imagine spending your professional life listening to dots and dashes, and then one evening, without warning, a violin begins playing in your ear. The gap between Morse code and voice is like the gap between smoke signals and a telephone call. The medium didn't just improve, it transformed into something qualitatively different, and the key to that transformation was modulation. The idea that you don't just turn a wave on and off, but use it as a carrier for continuously varying information. Let's understand this more carefully, because it's the foundation of everything that follows. To understand how this was done, you need to understand modulation, the principle without which all modern wireless communication would be impossible. An electromagnetic wave by itself carries no information. It just oscillates. A flat, monotonous sine wave stretching on forever, saying nothing. To make it speak, you have to encode information into it. You have to change something about it, make something variable. The earliest kind of modulation, amplitude modulation, AM, does this by varying the wave's amplitude. You take a high-frequency radio wave, your carrier, oscillating at, say, 1,000,000 Hertz. By itself, it carries zero information. Then you take the audio signal, a singer's voice, a violin, and use it to control the carrier's amplitude. When the sound gets louder, the carrier's amplitude increases. When softer, it decreases. The frequency of the carrier stays constant. Only the height of the wave changes, dancing to the rhythm of the sound. The receiver on the other end watches these amplitude changes and reconstructs the original audio. This is demodulation, the reverse process. AM radio has worked this way since the early 20th century and still does today. But AM has a serious flaw. It's extremely vulnerable to interference. Any electrical discharge, lightning, a car's ignition spark, an electric motor, creates an impulse that looks to the receiver like a sudden spike in amplitude. The receiver can't tell this spike from the real signal. The result? Clicks, crackle, static. Anyone who has listened to AM radio during a thunderstorm knows this. And that's where Edwin Howard Armstrong comes in. American engineer, obsessive, brilliant, stubborn to the edge of self-destruction. Armstrong invented several key circuit designs that made radio practical. The regenerative receiver, the super-regenerative receiver, and the super-heterodyne circuit, which remains the basis of virtually every radio receiver on the planet to this day. The super-heterodyne receiver, which Armstrong developed while serving in the Signal Corps during World War I, was perhaps his most enduring contribution. The principle is elegant. You take the incoming radio signal, at whatever frequency it happens to be, and mix it with a signal from a local oscillator inside the receiver. The mixing produces a new signal at a fixed, lower frequency, the intermediate frequency, or IF. This IF signal is then amplified and filtered. The beauty is that the amplifiers and filters only need to work at one fixed frequency, the IF, regardless of what frequency the radio is tuned to.
Changing the station just means changing the frequency of the local oscillator. The heavy lifting of amplification and selectivity happens at the IF, where you can build very precise, very efficient circuits. Before the super-heterodyne, if you wanted to receive different stations at different frequencies, you had to retune every amplifier stage, a fiddly, impractical process. Armstrong's super-heterodyne architecture became the standard by the 1930s and remains the standard today. Nearly every radio receiver on the planet, from a $5 FM radio to a satellite ground station, uses some variant of Armstrong's super heterodyne design. An idea from the trenches of World War I, still fundamental a century later. Armstrong also deserves more credit for understanding the relationship between bandwidth and signal quality.
In the course of developing FM, he demonstrated something counterintuitive. By using a wider bandwidth, trading spectrum space for signal quality, you could dramatically reduce noise. FM broadcast channels are about 200 kHz wide, compared to the 10 kHz of an AM channel. That wider bandwidth is part of why FM sounds so much cleaner. It's a trade-off. More spectrum per station, but vastly better audio. Armstrong proved this experimentally, and it was later formalized mathematically by Shannon's work on information theory. But his greatest contribution was frequency modulation, FM. Instead of changing the carrier's amplitude, FM changes its frequency. The amplitude stays constant. The frequency wobbles slightly around its nominal value. When the audio signal rises, the frequency nudges up. When it falls, the frequency nudges down. Why is this better? Because most interference, lightning, electrical discharges, motors, creates noise as amplitude spikes. An FM receiver ignores amplitude entirely. It listens only to frequency. A noise spike can blast the amplitude all at once. The receiver won't notice. The result? FM radio sounds cleaner, quieter, with far less noise. Armstrong demonstrated FM in the 1930s, and the sound quality was stunning. But here begins one of the most bitter stories in the history of technology. David Sarnoff, head of RCA and NBC, was Armstrong's friend. But AM broadcasting was making RCA enormous money. FM threatened to destroy the business model. Sarnoff did everything possible to delay FM's adoption. Years of legal battles followed. On the night of January 31st, 1954, Armstrong put on his overcoat, opened the window of his 13th floor New York apartment, and stepped out. He was 63. His widow continued the legal fights and eventually won nearly all of them. FM radio won. The FM band, 88 to 108 megahertz, is used worldwide today. But making waves carry information required more than modulation. It required amplification. And that brings us to the vacuum tube. In 1904, British physicist John Ambrose Fleming created the first vacuum diode, a tube that allowed current to flow in only one direction, useful for detecting radio signals. In 1906, American inventor Lee DeForest added a third element, a grid, between the cathode and anode, creating the triode. A small voltage on the grid could control a much larger current between cathode and anode. A weak signal in, a strong signal out. The tube amplified. Before the triode, receivers could only detect strong, nearby signals. With it, weak signals from distant stations could be amplified hundreds or thousands of times. Range exploded. And when Armstrong figured out that feeding part of the amplified signal back into the input, positive feedback, his regenerative circuit, the tube could also generate clean, stable, high-frequency oscillations. From a receiver, you could make a transmitter. A tube-based oscillator produced a pure tone on one specific frequency, unlike the chaotic broadband noise of a spark gap transmitter. Different stations could now work on different frequencies without drowning each other out. The transistor, invented at Bell Labs in 1947 by Shockley, Bardeen and Brattain, did everything the vacuum tube did: amplify, switch, oscillate, but was tiny, consumed almost no power, and didn't need to warm up. Transistors led to integrated circuits, which led to microprocessors. Your phone today contains billions of transistors, each performing the same basic function as De Forest's triode, only 1,000,000 times faster, 1,000,000 times smaller, and using 1,000,000 times less energy. And in the modern digital world, modulation has become incredibly sophisticated. Instead of simple AM or FM, we have phase shift keying, quadrature amplitude modulation, orthogonal frequency division multiplexing. These names sound intimidating, but they're all just different answers to the same question. How do you pack the most information into a given slice of spectrum with an acceptable error rate? In 1948, mathematician Claude Shannon formalized that question. His channel capacity theorem proved that for any communication channel, there's a theoretical maximum, the most information you can push through a given bandwidth at a given noise level. And you cannot exceed it, no matter how clever your modulation. Modern technologies like 5G have come frighteningly close to Shannon's limit. Further speed improvements will come not from cleverer modulation, but from accessing more spectrum, more bandwidth. And bandwidth is a finite resource.
Let's slow down on digital modulation for a moment, because it represents the most important shift in radio since the invention of radio itself. In an analog system, AM or FM, the shape of the transmitted signal directly mirrors the shape of the original sound. If a singer's voice gets louder, the amplitude or frequency deviation increases proportionally. There's a continuous, smooth link between the sound and the radio wave. And this creates a fundamental problem. Any distortion, any noise added to the signal along the way becomes permanently embedded. The receiver can't tell the original signal from the noise because both are just changes in amplitude or frequency. The farther the signal travels, the weaker it gets, the more noise accumulates. Analog signals degrade gradually and irreversibly. Digital modulation works differently. Instead of continuously varying a parameter, you switch it between discrete, sharply defined states.
The simplest case, binary phase shift keying, BPSK, flips the carrier's phase between 0 and 180 degrees. 0 degrees is a bit 0. 180 is a bit 1. The receiver doesn't need to measure the exact value of amplitude or frequency. It just needs to determine which of two states the signal is in, 0 or 1, yes or no. And here's the magic. As long as the noise isn't strong enough to turn a 0 into a 1, the receiver recovers the original data perfectly. Not approximately, not with degraded quality. Exactly, bit for bit. A digital signal is either received correctly or it isn't. There's no in between. And if errors do occur, error correction codes, extra check bits computed by mathematical rules and added to the data, let the receiver detect and even fix errors without retransmission.
This is why digital television looks equally sharp, regardless of distance from the transmitter, until the signal drops below the threshold, at which point the picture doesn't snow like analog. It breaks into blocks and vanishes. Threshold. All or nothing. More advanced digital modulations pack more bits per symbol. QPSK uses 4 phase states, 2 bits per symbol. 16QAM uses 16 states combining amplitude and phase, 4 bits per symbol. 256QAM uses 256 states, 8 bits. 1024QAM
used in Wi-Fi 6 and 5G, packs 10 bits per symbol. The more states, the more data per symbol, but the more sensitive the system is to noise because the distance between adjacent states shrinks. Shannon's theorem sets the ceiling. Maximum data rate equals bandwidth times the logarithm of 1 plus the signal-to-noise ratio. Increase power. Capacity grows, but logarithmically, ever slower. Increase bandwidth. Capacity grows linearly. But bandwidth is spectrum, and spectrum is finite. Modern systems operate within a few % of Shannon's limit. We've nearly wrung from the physics everything it allows. Further speed gains will come from more spectrum or denser frequency reuse, not from cleverer encoding. Which begins to answer our fourth big question. Why is empty space worth billions of dollars? But before we get to the economics of the invisible, we need to understand what happens to a wave after it leaves the transmitter. Because a radio wave flying through the real world encounters a gauntlet of obstacles, and each one changes its path, its strength, and its shape. Let's do a thought experiment. Imagine a specific radio signal, say the SOS call from the Titanic on the night of April 15, 1912.
Two radio operators, Jack Phillips and Harold Bride,
sending distress signals from a spark transmitter rated at somewhere between 1.5 and 5 kilowatts, depending on which historical source you trust. Morse code. 3 dots, 3 dashes, 3 dots, SOS. The wave left the Titanic's antenna and flew. At the speed of light, let's trace what happened to it. The first thing, instantly, in the first microsecond, the wave began losing strength. The reason is simple. It spread out in all directions. Imagine inflating a balloon. As the balloon grows, its surface area increases and its walls get thinner. Same with a radio wave. The energy that was concentrated at the antenna spreads over an expanding sphere. The sphere's area grows as the square of the distance, so signal power drops as 1 over distance squared. This is the inverse square law, and it's merciless. Twice the distance, 1/4 the power. 10 times the distance, 1/100th.
1,000 times. 1/1,000,000th. This law is one of the main reasons long-range radio is so difficult, and one of the main reasons antennas, especially directional antennas, matter so much. Second, part of the wave travelled along the surface of the Earth. This is called a ground wave or surface wave. At low and medium frequencies, the Titanic's transmitter operated at about 500 kHz, a wavelength of roughly 2,000 feet. Radio waves can crawl along the Earth's surface, following the planet's curvature. The wave interacts with the conducting surface, seawater in the Titanic's case, and bends around the horizon. The surface wave works best at low frequencies and over good conductors. Seawater is ideal. Over dry, sandy ground, it fades much faster. That's why ship-to-shore radio always worked better than over land, and why the Navy was first to embrace radio. Third, part of the wave flew upward toward the sky. And here, things get unpredictable.
Between about 40 and several hundred miles up, the Earth's atmosphere is ionized by ultraviolet radiation from the sun. Gas molecules lose electrons and become charged ions. This region, the ionosphere, acts as a kind of mirror for radio waves at certain frequencies. A wave that hits the ionosphere can be reflected back to Earth, like a ball bouncing off a ceiling. Whether a wave gets reflected or passes through depends on its frequency. Low frequencies, from a few tens of kilohertz up to roughly 30 megahertz, generally reflect. Higher frequencies, above 30 megahertz, generally pass through and escape into space. This means that short wave frequencies, 3 to 30 megahertz, can bounce off the ionosphere, return to Earth hundreds or thousands of miles away, bounce off the ground again, fly back up, making multiple hops around the planet. That's how ham radio operators talk between continents on small transmitters putting out just a few dozen watts.
And that's how Marconi's signal crossed the Atlantic in 1901, even though neither he nor anyone else understood the mechanism at the time. But the ionosphere is fickle. During the day, when the sun actively bathes the atmosphere, ionization is stronger and reflects higher frequencies. At night, ionization weakens, and only lower frequencies reflect. Ham operators know this. The 20-meter band, 14 megahertz, works best during the day. The 80-meter band, 3.5 megahertz, works best at night. There's a special technique called NVIS, Near Vertical Incidence Skywave, where a horizontal antenna sends the signal nearly straight up. It bounces off the ionosphere and falls back down, covering a regional area of a few hundred miles. Mountains, forests, buildings don't matter. The wave goes up and rains back down. NVIS works best on lower HF frequencies, the 80-meter and 40-meter bands.
The ionosphere changed our understanding of radio fundamentally. It explained why certain frequencies travel beyond the horizon and others don't. It explained why communication range varies with time of day and season. And it explained a phenomenon familiar to anyone who's listened to AM radio at night. You can pick up stations 1,000 miles away that are completely inaudible during the day. At night, the lower layers of the ionosphere weaken, and medium wave signals that were absorbed by those layers during the day begin reflecting off higher layers and making giant leaps across the continent. For ham radio operators, the ionosphere is simultaneously a blessing and a torment. It makes long-distance shortwave communication possible, but it's unpredictable. Sunspots, magnetic storms, time of day, season, everything affects the ionosphere's state.
Operators on the HF bands maintain an almost meteorological awareness of radio weather, checking solar activity indices, listening to propagation beacons on various frequencies, exchanging reports on which bands are open. The 40-meter band, 7 megahertz, is considered by many experienced operators as the Swiss Army knife of shortwave. With a horizontal antenna, it gives reliable regional coverage through NVIS, the near vertical incidence technique we mentioned. Signal goes straight up, bounces off the ionosphere, rains back down within a few hundred miles. With a vertical antenna, it provides long-range ionospheric skip to other continents. If a ham operator could have only one band, many would choose 40 meters because of this dual capability. The 20-meter band, 14 megahertz, is the workhorse for intercontinental communication. It's open most of the day as long as the sun sufficiently energizes the ionosphere. It's relatively reliable. Sailors use 14.3 megahertz for maritime communication nets. During periods of high solar activity, even higher bands, the 17-meter, 15-meter, 12-meter, and 10-meter bands, come alive with long-distance propagation. But during solar minimums, these upper bands can go silent for weeks. For emergency communication, they're not dependable. The 80-meter band, 3.5 megahertz, is the original telephone of amateur radio. Its wavelength of about 270 feet means antennas are long, about 135 feet for a half-wave dipole, but strung horizontally between trees, that's manageable. The 80-meter band excels at regional NVIS communication, reliable contact within a few hundred miles, day or night, regardless of terrain. Mountains, forests, buildings, none of them matter when the signal goes straight up and comes straight down. Above 30 megahertz, in the VHF range, the ionosphere is mostly transparent, and propagation is predominantly line of sight. But occasionally, atmospheric conditions create unexpected paths, sporadic E events, patches of intense ionization in the E layer of the ionosphere can briefly reflect VHF signals hundreds of miles. When this happens on the 6-meter band, around 50 megahertz, ham operators scramble to make contacts before the opening closes, which it does unpredictably, sometimes within minutes. The 6-meter band is sometimes called the magic band because of these sporadic, tantalizing openings. And then there's CB radio, Citizens Band, at 27 megahertz, right at the top of the HF range. CB was enormously popular in the United States in the 1970s and remains widely used by truckers.
Its 27 megahertz frequency is high enough that NVIS regional propagation doesn't work reliably, and skip propagation to distant locations depends heavily on solar conditions. During high solar activity, CB signals can skip thousands of miles, which creates both exciting long-range contacts and chaotic interference from distant stations. During quiet solar periods, CB is essentially limited to line of sight plus a modest ground wave, maybe 15 or 20 miles with a good antenna. The practical lesson from all of this: the choice of frequency is never arbitrary. Every frequency comes with its own propagation characteristics, its own antenna requirements, its own advantages and limitations. The invisible ocean has layers, and each layer has its own currents and tides. Now, above 30 megahertz, in VHF and UHF, the ionosphere is mostly transparent. Waves pass through and vanish into space. So the primary propagation mode is line of sight. Your FM station at 100 megahertz and your cell phone at 900 megahertz work this way. That's why cell towers stand on tall structures. The higher the antenna, the farther the line of sight. From about 160 feet up, the horizon is roughly 15 miles away. And that brings us to what happens when a wave meets something solid. And now we can fully answer our second big question: why some waves pass through walls and others don't. Because it comes down to these interactions. Reflection. Radio waves bounce off metal surfaces, like light off a mirror. In the real world, they constantly bounce off buildings, cars, wet pavement. A reflected signal can reach you around a corner. Useful, but it also arrives late relative to the direct signal, and the two can interfere, partly reinforcing, partly cancelling. This is multipath, and it's why your cell signal fades and flutters as you walk down a city street.
Refraction. When a wave passes between media of different density, its speed changes slightly and it bends. Temperature inversions in the atmosphere can create ducts that trap waves and carry them far beyond normal line of sight, hundreds of miles on VHF, where the usual range is maybe 30. Diffraction. A wave's ability to bend around obstacles. Longer wavelengths diffract more. AM radio waves, with wavelengths of 1,000 feet, flow around hills and buildings easily. Wi-Fi waves, with wavelengths of about 5 inches, barely bend at all. A building corner is a wall. Absorption. Some materials absorb radio energy and convert it to heat. Water is one of the best absorbers at microwave frequencies. That's why your microwave oven works at about 2.45 gigahertz. Water molecules resonate at that frequency. It's why rain weakens satellite signals, and it's why you lose Wi-Fi when there are water pipes between you and the router.
Your body, by the way, is about 60% water. When you hold your phone to your head, some radio energy is absorbed by your tissues, regulated by SAR safety standards. Interference. When two waves of the same frequency meet, they add up. Crests aligned, they reinforce. Crest meeting trough, they cancel. This creates complex, constantly shifting patterns of strong and weak signal. If your Wi-Fi works perfectly in one corner of a room and barely in another, that's almost certainly interference between the direct signal and its reflections. And there's one more environment where radio waves travel that deserves special attention: space. Satellite communication, GPS, and deep space links all involve signals crossing the vacuum between Earth and orbit. A geosynchronous satellite sits about 22,236 miles above the equator. At that altitude, its orbital period matches Earth's rotation. It hangs motionless over one spot.
3 such satellites can cover almost the entire Earth. Arthur C. Clarke, yes, the science fiction author, proposed this in a 1945 paper. Engineers called it fantasy. 20 years later, Earlybird, the first commercial geostationary communication satellite, launched. The drawback? Delay. A signal from Earth to a geostationary satellite and back travels about 44,500 miles. At the speed of light, that takes about 240 milliseconds, nearly a quarter of a second. Noticeable in phone calls, disastrous for online gaming. That's why low Earth orbit constellations like Starlink place satellites just a few hundred miles up. Latency drops to 20 or 40 milliseconds, but each satellite sees less territory and passes overhead in minutes, so you need thousands of them, continuously handing off to each other.
The Starlink ground terminal, a flat white panel about 20 inches across, nicknamed Dishy McFlatface by users, contains a phased antenna array. The same technology that started in Cold War radar installations shrunk to something you mount on a rooftop. Inside, hundreds of tiny antenna elements form and steer a beam electronically, tracking satellites as they pass overhead, handing off seamlessly from one to the next. No moving parts. The beam is steered entirely by adjusting phase relationships between elements. The same physics Hertz demonstrated with interference patterns in Karlsruhe, scaled up by 1 billion in complexity and shrunk down by 1,000 in size. The frequencies are Ku band, 12 to 18 gigahertz, and Ka band, 26 to 40 gigahertz. At these frequencies, rain becomes a problem. Drops are comparable in size to the wavelength and scatter the signal effectively. If your Starlink connection degrades during heavy rain, that's not a bug.
That's water-absorbing microwaves. Physics. The system compensates with adaptive modulation, trading speed for robustness when conditions deteriorate. But fundamentally, rain absorbs microwaves, and no engineering repeals that law. GPS works differently still. Each of about 30 satellites continuously broadcasts its identity and precise time from onboard atomic clocks. Your phone is only a receiver. It transmits nothing to the satellites. By measuring the arrival time of signals from several satellites and comparing them, it calculates its position. Accuracy depends on time precision. Light travels about 1 foot per nanosecond. To pinpoint your location within about 3 feet, you need nanosecond timing. And here's something remarkable. The software on GPS satellites includes corrections from Einstein's relativity. Clocks in orbit run differently than clocks on Earth, about 38 microseconds per day faster, due to combined effects of special and general relativity. Without correction, GPS accuracy would degrade by about 6 miles per day. Relativity isn't abstract. It's in the firmware of the satellite that helps you find the nearest coffee shop. GPS is, in many ways, the most elegant application of radio technology in everyday use. Let's walk through the physics one more time, slowly. because it pulls together almost every thread we've discussed. Each GPS satellite orbits about 12,500 miles above Earth, completing 2 orbits per day. The constellation currently consists of about 31 operational satellites, arranged so that at least 4 are visible from any point on Earth at any time. Each satellite carries multiple atomic clocks, rubidium and cesium, with accuracy better than 1 nanosecond per day. Each satellite continuously broadcasts a signal on 2 frequencies, L1 at 1575.42 MHz and L2 at 1227.6 MHz.
The signal contains the satellite's identity, the exact time according to its atomic clock,
and precise orbital data, so the receiver can calculate where the satellite is in space. Your phone's GPS receiver, a chip about the size of a grain of rice, picks up these signals from multiple satellites simultaneously. For each satellite, it measures the time delay between when the signal was sent, encoded in the signal itself, and when it was received, measured by the phone's internal clock. Multiply the time delay by the speed of light, and you get the distance to that satellite. With distances to 3 satellites, you can narrow your position to 2 possible points, the intersection of 3 spheres. With a 4th satellite, you resolve the ambiguity and also correct for errors in the phone's internal clock, which is far less accurate than the satellite's atomic clock.
In practice, GPS receivers track as many satellites as possible, often 8 to 12, and use all of them to compute a position with maximum accuracy. The signal itself is extraordinary in its weakness. By the time it reaches Earth from 12,500 miles up, the power density is about 10 to the minus 16th watts per square meter, roughly 100 billion times weaker than the signal from a modest FM radio station a few miles away. It's below the thermal noise floor. The receiver can only find it through correlation with the known spreading code, the direct sequence spread spectrum technique we discussed. Each satellite uses a different code, so the receiver can distinguish signals from different satellites, even though they're all on the same frequency. Modern GPS achieves civilian accuracy of about 10 feet. With augmentation systems, ground-based reference stations that broadcast corrections, accuracy improves to a few feet or even inches. Farmers use GPS to steer tractors along rows, accurate to within 2 inches.
Surveyors use it to measure land boundaries. Aircraft use it for precision approaches in poor visibility. All from a signal weaker than noise, traveling 12,500 miles from a satellite the size of a car, decoded by a chip smaller than your fingernail. And remember, those satellite clocks are adjusted for relativity. Without the 38 microsecond per day correction for combined special and general relativistic effects, GPS accuracy would drift by about 6 miles per day. Einstein's physics, proved in 1915, is coded into the firmware of every GPS satellite launched since 1978. There are more exotic propagation modes worth mentioning, because they show just how creative radio waves can be in finding paths through the world.
Tropospheric ducting. When a layer of warm air sits on top of cooler air, a temperature inversion, it can create an atmospheric waveguide. Radio waves get trapped between the Earth's surface and the warm layer and travel extraordinary distances. VHF and UHF signals that normally carry 30 or 40 miles can suddenly reach 300 or more. It's unpredictable and temporary, but when it happens, it's like the atmosphere is handing you a free long-distance call. Meteor scatter. When a meteor enters the atmosphere, it leaves behind a thin trail of ionized gas, plasma, that can reflect VHF radio waves for a few seconds. Ham operators send short bursts of data aimed at the meteor trail and catch the reflection hundreds of miles away. Each meteor is a tiny window of communication that opens and closes almost instantly. Some enthusiasts use digital modes that automatically package data into ultra-short packets and fire them the moment a meteor trail appears. And at the very edge of possibility, Earth-Moon-Earth communication, or moon bounce. You aim a powerful VHF or UHF signal at the moon. 1.3 seconds later, the time it takes light to reach the moon and return, a tiny fraction of that signal, reflected off the lunar surface, comes back. The round trip is about 477,000 miles. The delay is about 2.5 seconds. The returned signal is absurdly weak. But with large antennas and sensitive receivers, it works. People literally use the moon as a passive relay satellite. The same physics that Hertz demonstrated in a room in Karlsruhe scaled up to 250,000 miles. There's also the matter of what happens at very low frequencies, VLF, 3 to 30 kHz. These extremely long waves, with wavelengths measured in miles, can penetrate seawater to a depth of several dozen feet. That's why they're used for communication with submarines.
A submarine at shallow depth can receive a VLF signal from a shore-based transmitter. The bandwidth is vanishingly small. You might transmit a few characters per minute, but when you're trying to reach a nuclear submarine lurking under the ocean, a few characters is all you need. And about atmospheric absorption at specific frequencies, at 60 GHz, oxygen molecules in the atmosphere resonantly absorb radio waves. The signal attenuates by roughly 15 decibels per kilometer, roughly a factor of 30 for every kilometer traveled. Terrible for long-range communication, but useful for short-range links that need built-in privacy. The signal self-destructs with distance and can't cause interference to faraway systems. Some short-range wireless systems deliberately use 60 GHz for exactly this reason. Rain and moisture matter too. Below a few gigahertz, rain is essentially invisible to radio waves.
But at Ku-band satellite frequencies, around 12 GHz, heavy rain can noticeably weaken the signal. If you've ever lost satellite TV during a thunderstorm, that was rain absorption. The drops are comparable in size to the wavelength, and they scatter and absorb the wave efficiently. Engineers compensate with more transmit power and more sensitive receivers, but fundamentally, rain absorbs microwaves, and that's a law of physics no amount of engineering can repeal. You can only compensate. Every one of these phenomena, inverse square loss, ground waves, ionospheric skip, reflection, diffraction, absorption, multipath, is happening to every radio signal around you right now. Your cell phone call navigates all of them, every fraction of a second, without you noticing. And the device that bridges the gap between the radio circuitry and the outside world, the thing that turns electrical current into electromagnetic radiation and back again, is the antenna. Which brings us to our next big question. Why does the shape of a piece of metal matter so much? Your phone contains about a dozen different antennas. Each one is a different shape, a different size, tuned to a different frequency. One catches GPS from a satellite 12,500 miles up. Another catches Wi-Fi from a router 16 feet away. Another catches a cell tower a mile down the road. Another catches a Bluetooth earbud an inch from your ear. All working simultaneously, none interfering with the rest. How? The basic idea is deceptively simple. An antenna is a conductor, usually metal, shaped and sized so that when alternating current flows through it, it radiates electromagnetic energy efficiently. Or, in reverse, when electromagnetic waves wash over it, they induce a tiny alternating current that a receiver can amplify. That's it, that's the whole job.
But the details. how you shape the conductor, how long you make it, where you place it. That's where the art and science come in. The key insight: the most efficient radiation happens when the antenna's length is related to the wavelength of the signal. A half-wave dipole, a straight conductor whose total length is about half the wavelength, is one of the most fundamental and efficient antenna designs. Let's do the math. Broadcasting at 100 MHz, middle of the FM band, wavelength is about 9.8 feet. A half-wave dipole is roughly 5 feet. Manageable. Put it on a rooftop. But go down to AM frequencies, 1 MHz, and the wavelength is about 984 feet. A half-wave dipole would be nearly 500 feet of wire. You can't put that on a car. That's why AM stations use enormous tower antennas, those tall structures along highways with blinking red lights. In many cases, the tower itself is the antenna. The whole steel structure is energized and radiating. Typically about a quarter wavelength tall, using the ground beneath as an electrical mirror to create the missing other half of the dipole. As frequencies climbed higher, antennas got smaller. At 2.4 GHz, Wi-Fi, the wavelength is about 5 inches. A half-wave dipole is roughly 2.5 inches. That's why the antennas on your router are little plastic stubs, and why the antenna inside your phone can be a strip of metal a couple of inches long, hidden behind the case. There's one more thing about antennas that connects to our earlier discussion of wavelength in a way that's almost poetic. The ideal length of a half-wave dipole is exactly half the wavelength of the signal it's designed for. That means the antenna is physically resonant with the wave. It vibrates in sympathy with it, like a tuning fork vibrates when it hears its own note played nearby. When an electromagnetic wave at the right frequency washes over a half-wave dipole, the electrons in the metal oscillate back and forth in perfect step with the wave, building up the strongest possible current. A wave at a different frequency still moves the electrons, but less efficiently. The antenna is out of tune, like a guitar string that doesn't quite match the note you're singing. This resonance is why a quarter wave vertical on a car, tuned for FM at about 100 MHz, is roughly 2.5 feet tall, and why a quarter wave vertical for AM at 1 MHz would need to be about 240 feet tall, which is exactly why AM stations use tower antennas the size of small skyscrapers, and why a Wi-Fi antenna at 2.4 GHz is about 1.25 inches, and why an antenna for millimeter wave 5G at 28 GHz is a fraction of an inch, small enough that you can fit an array of them into a phone with room to spare.
The frequency determines the wavelength. The wavelength determines the antenna. The antenna determines the form factor of the device. This chain of causation flows directly from Maxwell's equations through 160 years of engineering into the physical shape of the object in your pocket. The reason your phone looks the way it does, why it's the size it is, why it doesn't have a telescoping whip antenna like a walkie-talkie, is fundamentally because the frequencies it uses have wavelengths of a few inches. If cell phones operated at AM frequencies, they'd need antennas hundreds of feet long. If they operated at visible light frequencies, the antenna would be smaller than a bacterium. The frequency we chose, or rather, the frequency that the physics of propagation, bandwidth, and antenna size conspired to make optimal, dictates the form of the technology. Physics shapes engineering. Engineering shapes objects. Objects shape daily life. And it all starts with 4 equations, written by a man in Edinburgh in 1865, describing waves he would never live to see.
But simple dipoles are just the beginning. The Yagi-Uda antenna, the classic TV antenna with a horizontal boom and parallel rods, was invented in the late 1920s by two Japanese engineers, Shintaro Uda and Hidetsugu Yagi. Only one rod, the driven element, connects to the transmission line. The others are parasitic elements. Some act as reflectors, bouncing energy forward, others as directors, pulling the radiation pattern in a specific direction. The result is significant gain in one direction, using nothing but carefully sized pieces of metal at specific spacings. No power, no electronics. The electromagnetic waves do all the work. The irony of the Yagi antenna's history is painful. During World War II, the Japanese military largely overlooked Yagi's work. The Allies didn't.
British and American radar engineers adopted Yagi designs extensively. When Japanese forces captured Allied radar equipment in Singapore in 1942, they found documents referencing Yagi antennas and reportedly had to ask, "Who is Yagi?" At microwave frequencies, parabolic dish antennas become possible. The familiar satellite dish. A parabolic curve has the geometric property that all incoming parallel waves reflect and converge at a single focal point. Put a small antenna element at the focus and you've got an incredibly sensitive, highly directional receiver. The gain is proportional to the dish area and inversely proportional to wavelength squared. Bigger dish, shorter wavelength, tighter beam. NASA's Deep Space Network uses 230-foot dishes to communicate with spacecraft billions of miles away. The Voyager probes, launched in 1977, are now in interstellar space. Their transmitter puts out 23 watts. The signal reaching Earth is about 1/10 of 1/4 of a watt. And we can still detect it, decode it, and extract scientific data. That's what a well-designed antenna system can do. And then there are phased arrays, perhaps the most important antenna technology of the modern era. Instead of one big antenna, you use many small ones in a grid. By carefully controlling the phase of the signal fed to each element, you can steer the combined beam in any direction, electronically in microseconds with no moving parts. The military developed phased array radar in the 1950s and 60s. Before them, radar had to physically rotate to scan the sky. Phased arrays could look everywhere, almost at once. And now the same technology fits inside your phone. Millimeter wave 5G at about 28 GHz has wavelengths of roughly 4/10 of an inch.
At that scale, you can fit an array of 8 or 16 antenna elements into a module smaller than a postage stamp. Your phone uses these tiny phased arrays to steer its beam toward the nearest tower, tracking it as you move, adjusting in real time. Cold War military radar technology shrunk down and mass-produced for a consumer device. Think about that for a second. There's a famous cautionary tale about phone antennas. In 2010, Apple released the iPhone 4, whose metal band around the edge served as the antenna. It was elegant, but if you held the phone a certain way, your hand bridged two antenna segments, causing the cell signal to collapse. Antenna gate. Steve Jobs suggested users just avoid holding it that way, which went about as well as you'd expect. Apple ended up distributing free cases to insulate the hand from the antenna. The human body, about 60% water, a decent conductor, is part of the antenna system whether engineers like it or not. Phone antenna designers test their designs with phantoms, head and hand models filled with fluid that mimics the electrical properties of living tissue. At the other end of the scale,
far from the tiny strips of metal inside phones, stand the largest antennas ever built. The Arecibo radio telescope in Puerto Rico was a parabolic dish 1,000 feet across, built into a natural limestone sinkhole in the mountains. For 57 years, from 1963 until it collapsed in 2020, it was the world's largest single-dish radio telescope. It could work both as a receiver, listening to radio waves from deep space, and as a radar, sending powerful pulses and catching reflections from planets, asteroids, and the ionosphere. It was replaced as the world's largest by China's FAST telescope, the 500-meter aperture spherical telescope, about 1,600 feet across, completed in 2016.
FAST is so sensitive, it can detect radio signals from pulsars, rapidly spinning remnants of exploded stars that emit narrow beams of radio waves like lighthouses. Each pulse from such a pulsar, a tiny ripple in the electromagnetic field arriving from thousands of light-years away, is captured by that enormous metal dish and converted into an electrical signal for computer analysis. Same physics, same Maxwell's equations, same Faraday induction, electromagnetic wave inducing current in a conductor. Just different scales, from a 2-inch strip catching Wi-Fi across a room to a 1,600-foot bowl listening to the whisper of dying stars thousands of light-years away. Every antenna we've discussed, from Marconi's 100-foot wires to the millimeter wave arrays in your pocket, does the same fundamental thing. It converts between electrical current and electromagnetic radiation. Faraday's induction, running in both directions, the same physics, just at different scales.
But antennas can only do their job if each radio system has its own slice of the electromagnetic spectrum to work in. And that finite, invisible resource, the radio frequency spectrum, turns out to be worth more than almost anything you can see or touch. In 2021, the Federal Communications Commission auctioned a strip of electromagnetic spectrum between 3.7 and 3.98 gigahertz. Telecom companies needed these frequencies for 5G. The auction brought in $81 billion. $81 billion. For the right to use a strip of nothing. This is our fourth big question answered in cold, hard cash. Why is empty space worth billions of dollars? A slice of invisible, intangible electromagnetic spectrum that you cannot see, cannot touch, and that physically is not a thing. Why does emptiness cost that much? To answer that, you need to understand one fundamental fact. The radio frequency spectrum is a finite resource.
Every radio system, every FM station, every cell phone, every Wi-Fi router, every satellite, every radar occupies a specific band of frequencies, a specific slice of spectrum. The width of that slice is the bandwidth. An FM station takes up about 200 kilohertz, a Wi-Fi channel 20 or 40 megahertz, a 5G channel up to 100 megahertz or more. Let's make this tangible with a real example. Think about FM radio in a city. The FM band runs from 88 to 108 megahertz, a total span of 20 megahertz. Each station needs a channel about 200 kilohertz wide, so in theory, you could fit 100 stations into the band. But in practice, stations in the same city can't use adjacent channels because some energy from a station's transmission spills into neighboring frequencies, a phenomenon called out-of-band emission or spectral leakage. You need a gap between stations.
In the US, FM stations are spaced 400 kilohertz apart, twice the channel width, to create buffer zones. And stations in the same geographic area need even more spacing to avoid interference when receivers aren't perfectly selective. The result is that a major city might have 20 to 40 FM stations, far fewer than the theoretical 100. And those allocations are carefully coordinated with neighboring cities. A station in New York on 97.1 MHz can coexist with a station in Philadelphia on the same frequency, only because the two cities are far enough apart that the signals, weakened by distance, don't overlap at a problematic level. This coordination applies to every radio service. Television channels are allocated so that adjacent channels aren't assigned in the same city.
Cellular carriers divide their licensed bands into channels and carefully plan which channels are used in which cells, ensuring that cells using the same frequency are far enough apart. Even Wi-Fi, in its unregulated band, has only 3 non-overlapping channels in the 2.4 GHz band, channels 1, 6 and 11 in the US numbering system. If you live in an apartment building with 30 Wi-Fi networks, at least 10 of them are sharing each channel and relying on the protocol's collision avoidance mechanism to take turns. This is why a radio engineer's job is fundamentally a job of managing scarcity. Every assignment of a frequency to a user means that frequency is unavailable to someone else, at least in that geographic area. Every new application, 5G, connected cars, Internet of Things devices, drone control links, demands its own slice of spectrum. And the spectrum doesn't grow. The laws of physics don't issue new frequencies on demand. So engineers find workarounds. Smaller cells allow more frequency reuse. Higher frequencies, despite their shorter range, offer more bandwidth. MIMO extracts multiple data streams from the same frequencies. Cognitive radio systems sense which frequencies are momentarily unused and opportunistically borrow them. Dynamic spectrum sharing allocates the same frequencies to different users at different times and places, managed by centralized databases. All of these techniques are, at their core, strategies for doing more with the same finite resource. They're the radio equivalent of intensive farming, extracting more yield from the same land. But just as there are physical limits to how much food an acre of soil can produce, there are physical limits, Shannon's limit, to how much data a hertz of spectrum can carry. We can approach those limits. We can get closer and closer with each generation of technology, but we cannot exceed them. The invisible ocean has a finite volume, and we're filling it up. If two stations try to broadcast on the same frequency in the same place, their signals overlap. The receiver hears a mess of 2 superimposed transmissions and can't decode either one. This is interference, and it's been the fundamental problem of radio since its birth. In the earliest days, the spectrum was the Wild West. Anyone could transmit on any frequency. As radio spread, the airwaves became chaos. The Titanic disaster in 1912, among other things, exposed this. The nearest ship, the Californian, had a radio, but its operator had gone to sleep. There was no requirement for round-the-clock radio watch. After the Titanic, governments began regulating the spectrum. Rules appeared. Who could transmit, on what frequencies, at what power. Licenses. Dedicated bands for different services. The history of spectrum regulation is worth a brief detour because it shows how a purely physical phenomenon became entangled with law, economics, and international politics. In the earliest days of radio, the 1900s and 1910s, the airwaves were a free-for-all. Anyone with a transmitter could broadcast on any frequency. This worked when there were a handful of stations scattered across vast distances. But as radio proliferated, the chaos became dangerous. The Titanic disaster crystallized the problem. Not only was there no requirement for ships to maintain round-the-clock radio watch, meaning the closest ship, the Californian, had its operator asleep, but the frequencies were cluttered with commercial traffic and amateur chatter that could have interfered with distress signals. In the aftermath, the Radio Act of 1912 required all seafaring vessels to maintain continuous radio watch and established basic rules for frequency use.
The 1920s brought commercial broadcasting, and with it, an explosion of news stations. In the United States, hundreds of stations went on the air with essentially no coordination. Two stations in the same city might broadcast on the same frequency, rendering both unintelligible. The Federal Radio Commission, established in 1927, began allocating frequencies and issuing licenses. Its successor, the Federal Communications Commission, founded in 1934, took over, and still manages the US spectrum today. Globally, the International Telecommunication Union, originally the International Telegraph Union, founded in 1865, the same year Maxwell published his electromagnetic theory, which is another lovely coincidence, coordinates spectrum allocation across nearly 200 countries.
The ITU's radio regulations, updated at World Radio Communication Conferences held every 3 to 4 years, constitute one of the most complex multilateral agreements in existence. They specify which frequencies are allocated to which services: broadcasting, mobile, satellite, radar, amateur, maritime, aviation, in which parts of the world. The negotiations are fiercely contested because spectrum allocation decisions affect industries worth trillions of dollars and national security interests of the highest order. And yet, the system works. Planes flying international routes can communicate with air traffic control in every country because everyone has agreed on the same aviation frequencies and protocols. Ships at sea can send distress signals on internationally recognized frequencies. Your cell phone can roam between countries because the spectrum allocations are harmonized.
This invisible cooperation, nearly 200 sovereign nations agreeing to share an invisible resource according to common rules, is one of the more remarkable achievements of international governance, and almost nobody knows it exists. The International Telecommunication Union, a UN agency, coordinates this globally, dividing the world into 3 regions and allocating frequencies for different services in each. This is perhaps one of the largest and least visible forms of international cooperation. Nearly 200 countries sharing an invisible resource so that one country's systems don't interfere with another's. Different parts of the spectrum have different value because not all frequencies are created equal. The whole usable spectrum is divided into bands. Very low frequency, VLF, 3 to 30 kHz. Wavelengths of 6 to 60 miles. These waves travel enormous distances along the Earth's surface and can penetrate seawater, so they're used for submarine communication. But the bandwidth is tiny, a few characters per minute at most. Medium frequency, MF, 300 to 3000 kHz. This is where AM broadcasting lives. Good ground wave propagation, especially at night, when ionospheric reflection strengthens and you can hear AM stations 1,000 miles away. High frequency, HF, 3 to 30 MHz, the legendary shortwave bands. Ionospheric skip allows these waves to travel around the planet. Ham radio operators talk between continents on a few dozen watts. CB radio lives here at 27 MHz. Very high frequency, VHF, 30 to 300 MHz. FM radio, television, aviation, and marine communications, the 2-meter ham band. mostly line of sight, but with good penetration through vegetation and some building materials.
Ultra-high frequency,
UHF, 300 to 3000 megahertz. Television, cellular, Wi-Fi, Bluetooth, GPS, all here. Perhaps the most congested part of the spectrum. Good throughput, manageable antenna sizes, but limited range and poor penetration through thick walls. Super high frequency, SHF, 3 to 30 gigahertz. Satellite communications, radar, microwave relay links, part of 5G. Extremely high frequency, EHF, 30 to 300 gigahertz. Millimeter waves. 5G uses part of this range. Enormous bandwidth, but very short range and heavy absorption by rain and foliage. Let's make bandwidth concrete. An FM radio station occupies a channel about 200 kilohertz wide. Within the FM band, 88 to 108 megahertz, that's a total of 20 megahertz of available spectrum. 20 megahertz divided by 200 kilohertz per station gives you a maximum of 100 stations in a given area.
In practice, you get fewer because adjacent stations in the same city need guard bands between them to prevent overlap, and neighboring cities must coordinate to avoid interference. But the point is that the FM band has room for about 100 stations, and that's it. No amount of engineering can create 101st. The spectrum is physically full. The same arithmetic applies everywhere. A single Wi-Fi channel at 20 megahertz of bandwidth can carry about 100 megabits per second under ideal conditions using modern modulation. Want more? Use a wider channel. 40 megahertz doubles the bandwidth and roughly doubles the speed. 80 megahertz doubles again. But each wider channel occupies more spectrum, and there are fewer of them available. In the 2.4 gigahertz band, which is only about 70 megahertz wide, you can fit 3 non-overlapping 20 megahertz channels. 3. In the 5 gigahertz band, which is wider, you can fit more.
In the new 6 GHz band opened for Wi-Fi 6E, wider still. But ultimately, the amount of data you can carry is proportional to the bandwidth you occupy, and there's only so much bandwidth to go around. This is the fundamental scarcity that makes spectrum valuable. You can't manufacture more of it. You can only use what exists more efficiently. Through frequency reuse, through more sophisticated modulation, through smarter protocols. And the closer we get to Shannon's theoretical limit, the less room for improvement remains. The low-hanging fruit has been picked. Every incremental improvement requires exponentially more engineering effort. That's why, when the FCC auctions a new band of spectrum, telecom companies bid tens of billions of dollars. They're buying the one thing that can't be created: room for more signals in the invisible ocean. See the pattern? Lower frequency, longer range, better obstacle penetration, but less data capacity.
Higher frequency, more data, but shorter range and worse penetration.
This is the fundamental trade-off of radio. There is no perfect frequency, only choices. The middle range, UHF, a few hundred megahertz to a few gigahertz, is the gold zone. Enough bandwidth for serious data. Enough wavelength to penetrate walls tolerably. Manageable antenna sizes. This is where cellular and Wi-Fi live. This is where the fiercest spectrum battles are fought. This is where auctions bring tens of billions. But engineers don't just wait for new frequencies. They've found ways to do more with what exists. And here's where we finally answer our fifth big question: how a dozen radio systems coexist in your phone without interfering? The answer is a combination of several techniques, each one elegant in its own right. Frequency reuse. Cellular networks divide territory into cells, each with its own base station. Neighboring cells use different frequency sets. Cells 2 hops apart reuse the same frequencies because the signal has weakened enough not to interfere. Smaller cells mean more reuse, more users. In dense urban areas, cells can be just a few hundred feet across. Spread spectrum. Instead of transmitting on one narrow frequency, you spread your signal across a wide band. One method, frequency hopping, was patented in 1942 by Hollywood actress Hedy Lamarr and avant-garde composer George Antheil. Lamarr, an Austrian émigré who'd fled a husband connected to the Nazis, understood radio-guided torpedoes. Antheil knew how to synchronize mechanical devices. Together, they designed a system where the frequency hopped through a sequence synchronized between transmitter and receiver, making jamming nearly impossible. The Navy didn't use it during the war, but decades later, spread spectrum became fundamental to cellular and Wi-Fi.
Bluetooth uses frequency hopping right now, jumping among 79 frequencies in the 2.4 GHz band, 1,600 times per second. GPS uses a related technique, direct sequence spread spectrum. The satellite signal is so weak it's actually below the noise floor, weaker than random static. The receiver knows the spreading code and uses correlation to extract the signal from noise, information pulled from below the noise. That's one of the most remarkable achievements in signal engineering. OFDM, orthogonal frequency division multiplexing, splits a wide channel into thousands of narrow subcarriers, each carrying a small piece of data simultaneously, like thousands of tiny stations operating in parallel. The math behind it uses the fast Fourier transform, rooted in Joseph Fourier's work on heat conduction in the early 1800s. Threads spanning centuries. There's one more aspect of the spectrum worth mentioning: the unlicensed bands.
Most spectrum is licensed, specific bands allocated to specific operators who paid for the right. But small slices are deliberately left open for anyone, subject to power limits. The most famous is the ISM band, at 2.4 GHz, originally reserved for industrial and medical equipment like microwave ovens. Wi-Fi, Bluetooth, and dozens of other technologies were allowed to move in, provided they tolerate interference from the ovens. In a typical apartment, dozens of Wi-Fi networks, Bluetooth devices, and maybe a microwave oven all share this one band. And somehow it all works, because the protocols are designed to share politely, sensing when the channel is busy and waiting for a gap. Radio waves can also be weapons. High-power microwave systems generate intense radio pulses that can disable electronics, computers, sensors, communication systems through unintentional ports of entry. Cables, seams, apertures. The US Air Force's Thor system can neutralize a swarm of drones with a single wide beam. Invisible, silent, speed of light. And the magazine is essentially unlimited. As long as there's fuel for the generator, it keeps firing. The physics of high-power microwave weapons connects directly to everything we've discussed about propagation and coupling. An HPM pulse travels at the speed of light, giving the target no warning and no time to react. Unlike a bullet or a missile, there's no flight time, no trajectory to track, no intercept opportunity. The beam is invisible and silent. The target simply stops working. The mechanisms of damage are well studied. When intense RF energy encounters electronic equipment, it couples into the circuits through any available path. Intentional antennas and receivers called front door coupling. but also through unintentional points of entry, cable shields, ventilation openings, display bezels, seams in enclosures.
These are backdoor paths, and they're nearly impossible to eliminate completely in any real-world device. The energy that gets in induces currents in circuit traces and components. If these currents exceed the damage threshold of semiconductor junctions, which can be surprisingly low, on the order of a few watts, the component fails. Permanently. The effects can be categorized on a scale. At the lowest levels, temporary interference that clears when the beam is removed. At medium levels, upset. The system crashes or locks up and requires operator intervention to restart, like a computer freeze. At the highest levels, permanent hardware damage requiring component replacement. The thresholds depend on frequency, pulse width, pulse repetition rate, and the specific vulnerability of the target electronics. This makes HPM effects inherently statistical. You can't guarantee a specific outcome, only probabilities. The military significance is profound.
A conventional weapon destroys one target per shot. An HPM weapon can potentially disable every piece of electronics within its beam, multiple targets simultaneously. The ammunition is electrical energy, which is cheap and abundant as long as the platform has fuel. The logistics of resupply, which are a critical constraint for conventional weapons, largely disappear. And the wide beam provides a high probability of hitting the target, unlike kinetic weapons or lasers that require precise aim. The challenge of protection is equally significant. In theory, enclosing electronics in a Faraday cage, a continuous metal shell, would block all external RF energy. In practice, every real device has openings: cooling vents, cable penetrations, display screens, access panels. Each opening is a potential point of entry,
And shielding done poorly can actually make things worse. Improperly placed shields can redirect and concentrate electromagnetic fields inside the equipment, increasing the energy density at certain points rather than reducing it. Effective hardening requires careful analysis and testing at design time. Retrofitting protection after a system is built is enormously expensive, 20 to 90% of the original system cost by some estimates, and often ineffective. There's even a non-lethal application. The active denial system uses millimeter waves at 95 gigahertz. At that frequency, radiation penetrates skin by a fraction of a millimeter and stimulates nerve endings, creating an intense sensation of burning. The person instinctively backs away. Turn off the beam, and the sensation stops immediately. Same electromagnetic waves as your Wi-Fi, just a different frequency, and a lot more power. Every electronic device is an unintentional radio transmitter. Every processor, every digital signal, every switching transistor creates high-frequency oscillations that can leak through wires and gaps and become radio interference for nearby devices. This is why strict electromagnetic compatibility standards exist. Every electronic device must be tested for emitted interference and for immunity to external electromagnetic fields before it can be sold. If you've ever heard clicking or buzzing in speakers when your phone was nearby, especially older models, especially just before a call, that was radio energy from the phone's transmitter coupling into the audio circuit through electromagnetic induction. The same effect Faraday discovered in 1831. A changing magnetic field induces current in a conductor. Only now the conductor is your audio cable picking up pulses from a GSM transmitter. Managing electromagnetic compatibility is one of the largest and least visible engineering challenges in modern electronics. Every wire in a device is a potential antenna, both transmitting and receiving. Engineers use shielding, filtering, grounding, careful circuit layout, and controlled impedance traces on printed circuit boards to keep unwanted radio emissions below regulatory limits and to keep external signals from disrupting the device's operation.
The metal cans you sometimes see soldered over sections of a phone circuit board. Those are EMI shields, tiny Faraday cages protecting sensitive circuits from internal and external radio noise. The fact that billions of electronic devices coexist on this planet, each one generating some radio noise, each one potentially susceptible to everyone else's noise, without the whole system descending into electromagnetic chaos, is a testament to the effectiveness of these standards and the engineers who implement them. It's an invisible discipline maintaining invisible order.
Software-defined radio, SDR, is perhaps the most quietly revolutionary development. Instead of building separate hardware for every frequency and protocol, you digitize the raw radio signal as early as possible and do everything else in software. One radio that can become any radio by changing the program. The US military needed this desperately. By the 1980s, the Army, Navy, Air Force, and Marines all had incompatible radio systems and literally couldn't talk to each other. During the Grenada invasion in 1983, an Army officer reportedly had to use a civilian telephone to call the United States and request naval gunfire support because his radio couldn't reach Navy ships offshore. Around 2012, hobbyists discovered that cheap $20 USB TV tuner dongles could be coaxed into working as general-purpose SDR receivers. Plug one into a laptop, attach a simple antenna, download free software, and suddenly you can tune across a huge swathe of spectrum and decode all kinds of signals: aircraft transponders, weather satellites, police radio, amateur radio, FM broadcasts. $20 and some curiosity, a window into the invisible world. The waterfall display, frequency on one axis, time on the other, signal strength as brightness, makes the radio spectrum literally visible. You can watch signals appear and vanish, see the rhythm of the invisible. From Hertz squinting at sparks in a darkened room to us staring at colorful cascades on a laptop screen, watching the entire radio spectrum breathe. The circle closes. And there's a historical footnote about spread spectrum that deserves more space. Hedy Lamarr, born Hedwig Eva Maria Kiesler in Vienna, was not just a Hollywood star.
Her first husband was Friedrich Mandl, an Austrian arms manufacturer with close ties to Mussolini and connections to the Nazi regime. Lamarr attended technical meetings with Mandl's clients and absorbed an unexpected amount about weapons systems, particularly radio-guided torpedoes and their vulnerability to jamming. She fled Mandl, escaped to London, and eventually reached Hollywood, where she became one of the biggest stars of the 1940s. But her mind never stopped working on the torpedo problem. At a dinner party, she met George Antheil, a composer known for his avant-garde works, including a piece for 16 synchronized player pianos. Antheil knew about mechanical synchronization. Lamarr knew about radio vulnerability. Together, they designed a system where the control frequency of a torpedo's radio guidance would hop through 88 frequencies, one for each key on a piano, synchronized by a mechanism similar to a player piano roll in both the ship's transmitter and the torpedo's receiver. An enemy trying to jam the signal would have to jam all 88 frequencies simultaneously, which was impractical. They received US patent number 2292387 in August 1942. The Navy didn't use it during the war. The technology to implement it was too bulky. But the fundamental concept, spreading a signal across many frequencies to resist jamming and interference, became one of the pillars of modern wireless communication. CDMA, cellular networks, Wi-Fi, Bluetooth, GPS, all used descendants of spread spectrum. Lamarr received belated recognition near the end of her life, including the Electronic Frontier Foundation's Pioneer Award in 1997.
She died in 2000, at 85. The most famous face of the 1940s also held one of the most important wireless patents of the 20th century. The story of SDR, software-defined radio, also deserves a bit more context. The US military's interoperability problem was real and consequential. The Joint Tactical Radio System, JTRS, pronounced JITRS, was supposed to create a family of software-defined radios that could be reprogrammed on the fly to communicate across all branches and with allied forces. The program ran for years, cost billions, and was eventually restructured because the technology and ambitions didn't quite align with the budget. But the underlying idea was sound. It pushed the entire industry forward.
What made SDR accessible to ordinary people was the discovery around 2012 that certain cheap USB TV tuner dongles, little sticks you'd plug into a laptop to watch digital television, costing about $20, contained a chip called the RTL2832U that could be coaxed into working as a general-purpose SDR receiver. You plug one into your computer, attach a wire antenna, download free software, and you can tune across a huge swath of the radio spectrum. Aircraft transponders broadcasting position and altitude in real time. Weather satellite images received directly from polar orbiting NOAA satellites as they pass overhead. Amateur radio conversations, pager networks, trunked radio systems. All from a device that costs less than a large pizza. The waterfall display, frequency on the horizontal axis, time scrolling vertically, signal strength shown as color, makes the invisible visible. You can watch FM stations standing as steady pillars on their frequencies.
See the short bursts of trunked radio communications pulsing. Watch digital data packets flickering. See the quiet, even glow of thermal noise. The fundamental electromagnetic whisper generated by the random motion of electrons in every conductor, always present, always there. This was the modern equivalent of the crystal set receivers that kids built in the 1920s. A wire, a galena crystal, a razor blade, and suddenly you were pulling voices out of thin air. The RTL-SDR dongle gave a whole new generation a window into the invisible world of radio, and it cost $20. Let's pull back for a moment and look at the whole picture. Because behind all these frequencies and modulations and protocols lies something astonishing. An invisible architecture that wraps around the entire planet. Imagine you could see radio waves, that your eyes could perceive not just the narrow stripe of visible light, but the entire electromagnetic spectrum. You'd see every cell tower, millions of them worldwide, pulsing with energy, directing beams to thousands of phones. You'd see Wi-Fi routers flooding rooms with spheres of radio energy at 2.4 and 5 gigahertz, signals bouncing off walls and ceilings, creating intricate interference patterns. You'd see GPS satellites drifting across the sky, 12,500 miles up, each whispering a signal so faint it's below the noise floor, and billions of receivers on Earth quietly listening. You'd see radars sweeping, weather radars tracking storms, aviation radars tracking planes, military phased arrays tracking hundreds of targets simultaneously. You'd see shortwave signals arcing up to the ionosphere and bouncing back, covering thousands of miles. You'd see Bluetooth connections, tiny pulses hopping across 79 frequencies, 1,600 times per second, linking phone to earbuds, laptop to mouse.
And beneath it all, the quiet, uniform, ancient glow of the cosmic microwave background. 13.8 billion years old. The oldest light in the universe. Still traveling. Still passing through you. All of this architecture is invisible. No human sense organ can detect any of it directly. We built the whole thing blind, using mathematics, experiments, and instruments that extend our perception beyond what we were born with. And it works. Every second, simultaneously serving billions of devices, each finding its own quiet corner in the invisible space. Now, let's follow one signal through this architecture, from your mouth to your friend's ear, to see how all the pieces fit together. You pick up your phone and call someone 500 miles away. Your voice, sound waves in air, hits the microphone and becomes an electrical signal. This analog signal is immediately digitized, sampled 8,000 times per second, each sample recorded as a number.
Your voice is now a stream of bits, zeros and ones. The stream is compressed, error correction bits are added, and the whole packet is modulated onto a radio carrier at, say, 1900 MHz, using OFDM with 64 QAM modulation spread across thousands of subcarriers. The resulting signal is amplified to about 200 milliwatts, 0.2 of a watt, 5,000 times less than the bulb in your refrigerator, and fed to the antenna. The antenna radiates an electromagnetic wave. A tiny strip of metal, a couple of inches long, hidden behind glass and plastic, creates a ripple in the electromagnetic field. The same ripple Maxwell predicted and Hertz discovered. The wave flies outward. It reaches the nearest cell tower, maybe 1,000 feet away, maybe a mile. Along the way, it bounced off several buildings, passed through a wall, was weakened by a tree, interfered with its own reflections.
The tower's receiver, using MIMO algorithms, separates the direct signal from reflected copies, suppresses interference from other phones, extracts your data and decodes it. From there, your data travels by fiber optic cable to a switching center, across a trunk line to another city, to another base station, which modulates it back onto a radio wave and transmits it to your friend's phone. Here's something most people don't realize about their cell phone. It's constantly transmitting, even when you're not making a call. Your phone maintains a continuous, low-level conversation with the nearest cell tower, exchanging status updates, timing synchronization, and location information. The tower needs to know you're there, so it can route incoming calls and messages to you. Your phone needs to know where the tower is, so it can connect quickly when you initiate a call. As you move, walking, driving, your phone monitors the signal strength from surrounding towers and reports back. When the signal from a new tower becomes stronger than the one you're connected to, the network executes a handover. Your connection is seamlessly transferred from one tower to the next without interruption. In a moving car, this can happen every few seconds. You never notice because the process takes milliseconds and is coordinated between the old and new tower before the switch happens. Your phone also automatically manages its own transmit power. When you're close to a tower, it transmits at minimum power, just a few milliwatts, to conserve battery and minimize interference with other users. When you're far away or behind obstacles, it ramps up to maximum, usually about 200 milliwatts, or about 1/5 of a watt. The tower tells the phone what power level to use, adjusting it continuously.
This power control is crucial for the cellular system to work. If every phone transmitted at full power all the time, they'd create so much interference that the system would collapse. Modern phones can also operate on multiple frequency bands simultaneously and switch between them dynamically. If the millimeter wave 5G connection drops because you walked indoors, the phone seamlessly falls back to a lower frequency band, maybe 900 MHz, that penetrates walls better. It's slower, but it works. The phone juggles these transitions dozens of times per minute, completely invisibly. And through all of this, the phone is also maintaining Wi-Fi and Bluetooth connections, listening to GPS satellites,
and occasionally performing NFC transactions if you wave it at a payment terminal.
A dozen radios in a device that fits in your palm, each one finding its own slice of the invisible spectrum and maintaining its own conversation, choreographed by baseband processors executing billions of operations per second. Every piece of this system traces back to the principles we've discussed tonight. And that's not a simplification, that's literally true. Their phone demodulates, decodes, decompresses, converts bits back to analog, and drives the speaker. Air vibrates. Your friend hears your voice. The entire journey, mouth to ear, takes about 50 to 100 milliseconds, a tenth of a second. Faster than a blink. 500 miles, and you don't even notice. Every element of that chain traces back to something we've discussed. The microphone, Faraday's electromagnetic induction, digitization, Shannon's sampling theorem, modulation, OFDM based on Fourier's transform, the antenna, a scaled-down half-wave dipole, propagation, all the phenomena we covered,
Error correction, coding theory inspired by Shannon. And at every step, Maxwell's equations describing every interaction between the wave and the world. Let's unpack the cellular part a bit more, because the engineering that happens in that fraction of a second is staggering. When your phone transmits, it doesn't just shout into the void. It engages in an elaborate dance with the base station. The phone and tower continuously exchange control signals. The tower tells the phone which frequency to use, at what power level, and what modulation scheme. If you're close to the tower and the signal is strong, the system uses a high-order modulation, maybe 256 QAM, packing 8 bits into each symbol. High speed, but vulnerable to noise. If you're far away or behind obstacles and the signal is weak, it drops to a lower modulation, maybe QPSK, 2 bits per symbol. Slower, but much more robust.
This adaptation happens hundreds of times per second, continuously optimizing the trade-off between speed and reliability. And MIMO, multiple input, multiple output, deserves more attention. Traditional radio uses one antenna on the transmitter and one on the receiver. Single in, single out. MIMO uses multiple antennas on both ends, and instead of treating multipath reflections as interference to be suppressed, MIMO exploits them. Each path between each pair of transmit and receive antennas carries a slightly different version of the signal. With clever math, specifically matrix algebra and singular value decomposition, the receiver can separate these versions and extract multiple independent data streams from what looks like a jumble of overlapping signals. It's as if the multipath-rich urban environment, which used to be the enemy of reliable communication, became a multi-lane highway.
In 5G, massive MIMO uses dozens or even hundreds of antenna elements on the base station, creating dozens of simultaneous beams directed at different users. Each beam is electronically steered using phased array principles. The base station can serve many users on the same frequency at the same time, as long as they're in slightly different directions. Spatial multiplexing. It's another way to squeeze more capacity from the same spectrum without needing more bandwidth. The amount of signal processing required to do this is enormous. Every fraction of a second, the system is solving matrix equations, estimating channel characteristics, adapting modulation, managing interference, correcting errors. Your phone's baseband processor, the chip that handles all this radio math, executes billions of operations per second, dedicated entirely to maintaining your connection. And it does this while consuming a fraction of a watt.
Billions of transistors, each one a descendant of DeForest's triode, switching on and off billions of times per second.
all in the service of turning your voice into invisible waves and back again. 200 years of science and engineering compressed into 1/10 of a second of conversation. And here we are, at the bottom. We've come the whole way, from the surface, Wi-Fi and Bluetooth, everyday things you never think about, through FM radio and television, through cellular networks and their cellular geometry of frequency reuse, through the shortwave world of ionospheric skip and midnight signals traveling thousands of miles, through surface waves crawling along the ocean, past enormous parabolic dishes catching the whisper of Voyager at the edge of the solar system, down to the very bottom. The remnant radiation of the Big Bang, 13.8 billion years old. Remember the questions we asked at the beginning? Let's count them off.
What actually is a radio wave? A ripple in the electromagnetic field, electric and magnetic fields leapfrogging through space at the speed of light. The same phenomenon as visible light, just at a lower frequency. Maxwell figured that out in 1865. Why can some waves pass through walls while others can't? Because wavelength determines how a wave interacts with obstacles. Long wavelengths flow around and through things. Short wavelengths are blocked by anything comparable to their size. The same diffraction physics that governs ocean waves around a breakwater. How do you encode information into an invisible wave? Modulation, varying the amplitude, or the frequency, or the phase of a carrier wave in time with the information you want to send. AM, FM, and their digital descendants, all the way to the OFDM and QAM schemes that 5G uses, each one a more sophisticated answer to the same basic question. Why is empty spectrum worth billions?
Because the spectrum is finite, because signals on the same frequency interfere with each other, and because Shannon's theorem puts a hard ceiling on how much data you can push through a given bandwidth. More data requires more spectrum, and there's only so much spectrum to go around. How does your phone run a dozen radios without them interfering? Careful frequency planning, orthogonal signal processing, sophisticated filtering, power management, and phased array beam steering. Each system occupying its own tiny slice of the spectrum, each protocol designed to coexist politely with the others. Every answer traces back to the same source. 4 equations written by a Scottish physicist in 1865, describing a field that was already 13 billion years old when he wrote them down. One phenomenon, one set of equations. 4 lines of mathematics written by Maxwell in 1865. One electromagnetic field, filling all of space since the beginning of time.
Every system we've discussed tonight, every radio, every television, every phone, every satellite, every radar, stands on a pyramid of knowledge that reaches back to Ørsted and his compass needle, to Faraday and his lines of force, to Maxwell and his 4 equations, to Hertz and his sparks in a dark room. And from them, through Marconi and Fessenden and Armstrong and Shannon and Lamar and Yagi and Uda and countless engineers whose names are lost, to the device in your pocket that simultaneously maintains a dozen radio links on different frequencies, and none of them interfere with the rest. And here's perhaps the most striking thing about all of it. Some of the very first radio waves ever created by humans are still flying. Those crude spark gap transmissions from Karlsruhe in 1887, they're now more than 139 light-years from Earth. Impossibly faint, almost certainly undetectable, but technically still out there, still propagating, still carrying the ghost of a signal through interstellar space. The Titanic's distress calls from 1912, more than 114 light-years out. Armstrong's first FM broadcasts from Alpine, New Jersey, about 90. All still traveling, all still out there in the dark between the stars, getting fainter and fainter but never quite gone. And that's a nice thought to fall asleep to, isn't it? That every signal ever transmitted is still out there somewhere, spreading outward in an ever-expanding sphere. Hertz's first experiments, Marconi's first transatlantic transmission, Fessenden's Christmas Eve broadcast of 1906, the distress calls from the Titanic, Armstrong's first FM broadcasts. All of it, still traveling, still out there in the dark. And you know, there's something quietly moving about this whole story. Think about Edwin Howard Armstrong, standing on the 13th floor of his apartment building on that winter night in 1954, exhausted from years of legal battles, feeling like the world had stolen his life's work. If he could have seen what FM became, not just the FM radio band, but the principle of frequency modulation woven into countless communication systems, the mathematical descendants of his ideas embedded in every modern digital radio, would it have changed anything for him? Probably not. The pain was personal, not technical. But his work endured. His ideas won, even if he didn't live to see the victory. Or think about Heinrich Hertz, who died at 36, only 6 years after his groundbreaking experiments, never knowing that the waves he demonstrated in that small laboratory in Karlsruhe would reshape civilization. "It's of no use whatsoever," he said. "Just an experiment that proves Maestro Maxwell was right. Just an experiment." Just the foundation of everything we've talked about tonight. That's the thing about fundamental discoveries. The people who make them often can't see where they'll lead, because the path from discovery to application is never straight. It winds through other people's workshops and laboratories and garages, through wars and economic booms and regulatory fights, through failures and accidents and stubborn persistence. Maxwell couldn't have predicted Marconi. Marconi couldn't have predicted Armstrong. Armstrong couldn't have predicted Shannon. Shannon couldn't have predicted that his information theory would enable a teenager in Tokyo to stream video on a phone while riding a bullet train. Each generation builds on what came before, often without fully understanding the foundations they're standing on. And that's okay. That's how it works. That's how it's always worked. The room is quiet now, but it's full of waves. It always has been.
You don't need to think about any of this anymore. You don't need to remember the frequencies, or the names, or the dates. They'll be there if you want them later. For now, just know that the air around you is humming with 2 centuries of human ingenuity. Every wave in this invisible ocean is a small monument to someone who asked the right question. Ørsted, who moved a compass needle near a wire. Faraday, who imagined lines of force. Maxwell, who turned them into 4 equations. Hertz, who found sparks in the dark. Marconi, who sent a signal across the ocean. Armstrong, who invented FM and didn't live to see it win. Shannon, who calculated the limit. And tens of thousands of engineers whose names we'll never know, whose work, right now, right here, is passing through you as invisible waves.
The air around you is full of these waves, and it asks nothing of you. It just passes through, gentle and constant, like a tide you can't see or hear or feel, carrying everything we've ever wanted to say to each other. Everywhere, all at once, at the speed of light. Let it carry you off to sleep. Breathe. Rest. The waves will take care of everything else.